Właśnie teraz, gdy tego słuchasz, w naszym Układzie Słonecznym dzieje się coś bezprecedensowego. Od czasu odkrycia, trzypień Atlas w lipcu, sprawy stają się coraz dziwniejsze. Ten starożytny międzygwiezdny gość od samego początku zadziwiał astronomów, ale jego niemożliwa chemia i zielony blask nie są już najdziwniejszą częścią. Najdziwniejszą częścią jest to, co dzieje się w jego śladzie. Nasza zazwyczaj przewidywalna kosmiczna okolica zamieniła się w ruchliwą autostradę zbieżnych obiektów z wzorcami gromadzenia się, które przeczą prawdopodobieństwu. Od roju 7 komet przybywających razem do nowej fali asteroid, przelatujących obok Ziemi, to, co widzimy na nocnym niebie, jest dalekie od normalności. A teraz astronomowie nie mają wyboru, jak tylko zacząć pytać, co tak naprawdę 3 Atlas robi z naszym Układem Słonecznym. Zostań ze mną w tej nocnej eksploracji, a odkryjemy, czy jesteśmy świadkami największego zbiegu okoliczności w galaktyce, czy czegoś znacznie bardziej doniosłego. Część pierwsza nadchodzi fala asteroid. Połowa września 2025 roku miała być spokojna, po prostu kolejny miesiąc rutynowego ruchu kosmicznego, który astronomowie katalogują z mechaniczną precyzją, zanim przejdą do kolejnej obserwacji. Ale wszechświat miał inne plany. To, co wydarzyło się w tych rześkich jesiennych tygodniach, było czymś zupełnie innym. Niebiańska parada, która zmusiła naukowców do pośpiechu do teleskopów, a opinię publiczną do zastanawiania się, czy jesteśmy świadkami czegoś więcej niż zwykłego zbiegu okoliczności. Najpierw przybył główny bohater, asteroida 2025 FA-22, góra skał o rozmiarach od 130 do 290 metrów. 18 września przeleciała obok Ziemi w odległości nieco ponad 2 odległości księżycowych, czyli około 835 tysięcy kilometrów. Wystarczająco blisko, by trafić na pierwsze strony gazet, wystarczająco daleko, by pozwolić nam spokojnie spać. Ale tutaj historia staje się interesująca. FA-22 nie przyszła sama. To nie była typowa asteroida samotnego wilka pojawiająca się zgodnie z planem. Zamiast tego to bardziej przypominało otwarcie kosmicznego teatru z wieloma wykonawcami wchodzącymi na scenę w szybkim tempie. Mały obiekt bliski Ziemi 2025 RJ-2 już wszedł 3 dni wcześniej, 15 września, przelatując w odległości zaledwie 0,78 odległości księżycowych, zaledwie 300 tysięcy kilometrów od naszych drzwi. W kategoriach astronomicznych to praktycznie uścisk dłoni. Ale to nie były odosobnione incydenty. Przez cały ten sam tydzień dziesiątki dodatkowych gości w odległości subksiężycowej malowały swoje trajektorie w naszej lokalnej okolicy. Każdy z nich skatalogowany i śledzony przez globalną sieć systemów nadzoru kosmicznego. Był to typowy ruch pod względem liczbowym. Jednak coś w tym zgrupowaniu było inne. Czas wydawał się niemal wyreżyserowany, jakby ci starożytni wędrowcy skoordynowali swoje przybycie dla maksymalnego efektu dramatycznego. Następnie pojawiła się obsada drugoplanowa. Kometa C 2025 R2, odkryta przez instrument SWAN na pokładzie statku kosmicznego SOHO 11 września, zaczęła jaśnieć w kierunku widzialności gołym okiem w pobliżu konstelacji Panny. Jej warkocz rozciągał się po wieczornym niebie niczym kosmiczne pociągnięcie pędzla, widoczny dla każdego, kto wiedział, gdzie szukać, gdy zmierzch ustępował ciemności. Los komety poza peryhelium pozostawał niepewny. Wiele takich obiektów fragmentuje się pod intensywnym nagrzewaniem Słońca, pozostawiając jedynie świecące ślady gruzu jako pomniki ich krótkich gwiezdnych karier. W międzyczasie w tle każdego astronomicznego raportu prasowego czaiła się inna znajoma twarz Apophis, oficjalnie oznaczona 99 942. Apophis to asteroida, która kiedyś znajdowała się na szczycie każdej listy obaw dotyczących obrony planetarnej. 400-metrowa góra skał, zaplanowana na niepokojąco bliskie spotkanie z Ziemią 13 kwietnia 2029 roku. Ten przelot zbliży Apophis na 32 000 kilometrów od powierzchni naszej planety, bliżej niż nasze satelity geostacjonarne, wystarczająco blisko, by zobaczyć ją gołym okiem, gdy pędzi po nocnym niebie z prędkością 50 000 kilometrów na godzinę. Ale prawdziwa gwiazda tego niebiańskiego widowiska wciąż czekała za kulisami. Ukryte wśród rutynowych ogłoszeń o odkryciach było coś bezprecedensowego. 3PR Atlas, znana również jako CED 2025N1, odkryta 1 lipca 2025 roku przez zespół Atlas w Chile. Ten obiekt różnił się od wszystkiego innego, co we wrześniu zatarasowało nasze teleskopy. To nie była kolejna asteroida, ani kometa z naszej lokalnej rodziny Układu Słonecznego. To było coś znacznie bardziej egzotycznego. Międzygwiezdny gość, zaledwie trzeci kiedykolwiek potwierdzony, niosący chemiczne sygnatury, które podważyłyby wszystko, co myśleliśmy, że wiemy o formowaniu się planet. Zespół Atlas początkowo dostrzegł ją jako kolejną rozmytą kropkę, poruszającą się na tle pola gwiazd. Ale w miarę jak dalsze obserwacje dopracowywały jej trajektorię, matematyka opowiedziała niezwykłą historię. Ten obiekt podróżował po hiperbolicznej orbicie, co oznaczało, że posiadał więcej niż wystarczającą prędkość, aby całkowicie uciec z grawitacyjnego uścisku naszego Słońca. Przybył skądś indziej, z innego układu gwiezdnego, być może oddalonego o lata świetlne, i po krótkim spotkaniu z naszym sąsiedztwem słonecznym będzie kontynuował swoją podróż w kosmiczną ciemność, nigdy nie wracając. Co jeszcze bardziej niezwykłe, w 3 oczach Atlas to jego czas. Peryhelium zaplanowano na koniec października 2025 roku, zaledwie kilka tygodni po wrześniowej paradzie asteroid. Następnie niczym artysta schodzący ze sceny zniknie w blasku Słońca, ukryty przez przytłaczającą jasność naszej gwiazdy. Ale cierpliwość zostanie nagrodzona. Na początku grudnia, gdy ruch orbitalny Ziemi przeniesie nas w lepszy kąt widzenia. 3 oczy. Atlas ponownie wyłonią się zza kurtyny Słońca, oferując teleskopom najlepszą okazję do zbadania autentycznego kawałka międzygwiezdnej nieruchomości. Okno obserwacyjne było idealne, aż za idealne, jak niektórzy mogliby powiedzieć. W najbliższym zbliżeniu w grudniu obiekt będzie nadal oddalony o 1,8 jednostek astronomicznych, czyli około 270 milionów kilometrów od Ziemi, wystarczająco daleko, aby nie stanowić żadnego zagrożenia, wystarczająco blisko, aby nasze najpotężniejsze instrumenty mogły przeprowadzić szczegółową analizę spektroskopową. To było tak, jakby wszechświat dostarczył starannie zapakowaną próbkę z innego układu gwiezdnego prosto na nasz astronomiczny próg wraz z optymalnymi warunkami obserwacyjnymi i swobodnym harmonogramem badań. Ale dlaczego teraz? Dlaczego ten nagły przypływ kosmicznej aktywności gromadzącej się wokół tych samych kilku tygodni? Lepsze badania z pewnością odegrały rolę. Obserwatorium Very C. Rubin właśnie uchwyciło swoje pierwsze obrazy świetlne w czerwcu 2025 roku, wykrywając tysiące nowych asteroid w około 10 godzin pracy. Coraz więcej oczu skanowało niebo z większą czułością niż kiedykolwiek wcześniej, ujawniając prawdziwą gęstość zaludnienia małych ciał naszego Układu Słonecznego. Jednak ten czas wydawał się zbyt wygodny, zbyt zaaranżowany, by zbyć go jako zwykłe błędy obserwacyjne. Czy wrzesień 2025 roku był czymś szczególnym? Jakaś grawitacyjna konfluencja lub sezonowe wyrównanie, które wciągnęło te obiekty w zbieżność? Czy też byliśmy świadkami pierwszego aktu czegoś większego kosmicznego dramatu, rozgrywającego się w skalach czasowych, znacznie przekraczających ludzkie postrzeganie? Nastrój wśród astronomów nie był strachem, ale pilną ciekawością. Systemy obrony planetarnej znacznie ewoluowały od czasów, gdy uderzenia były wyłącznie domeną filmów katastroficznych. Posiadamy teraz możliwości technologiczne do śledzenia, charakteryzowania, a nawet odchylania potencjalnie niebezpiecznych obiektów. Ostatni sukces misji DART NASA udowodnił, że kinetyczne impaktory mogą skutecznie zmieniać trajektorię asteroidy, podczas gdy misja Hera Europejskiej Agencji Kosmicznej jest w drodze, aby dokonać analizy kryminalistycznej wyników. ale wiedza i przygotowanie są tylko tak dobre jak czas ostrzegania, jaki zapewniają. A to rodziło niewygodne pytania dotyczące gości, których jeszcze nie widzieliśmy, tych, którzy wciąż zbliżają się od strony Słońca, ukryci w blasku aż do ostatecznego zbliżenia. Gdyby FA-22 znajdowała się na kursie kolizyjnym zamiast bezpiecznego przelotu, czy mielibyśmy wystarczająco wczesne ostrzeżenie, aby podjąć skuteczną reakcję? I co 3 oczy, Atlas z jej obcą chemią i międzygwiezdnym pochodzeniem, mówi nam o niewidocznej populacji obiektów dryfujących między gwiazdami. Wrześniowy przypływ obudził coś w zbiorowej świadomości naukowej. To nie była panika, to było uznanie, że nasz Układ Słoneczny był znacznie bardziej aktywny, znacznie bardziej połączony z szerszą galaktyką, niż wcześniej sobie wyobrażaliśmy. Byliśmy świadkami otwarcia aktu przejścia ludzkości z gatunku jednej planety do aktywnych uczestników zjawisk o skali galaktycznej. Ale najpierw musieliśmy zrozumieć, z czym tak naprawdę mieliśmy do czynienia. Gdyby FA-22 uderzyła w Ziemię, zamiast bezpiecznie przelecieć, jak wyglądałoby to uderzenie? Część druga, głębokie zanurzenie w FA-22. Co by się stało, gdyby uderzyła? Matematyka kosmicznej kolizji jest bezlitosna. Kiedy asteroida 2025 FA-22 przeleciała obok Ziemi 18 września w odległości 835 tysięcy kilometrów, niosła ze sobą energię kinetyczną równą około 100 megaton TNT. Aby to ująć w perspektywie, to około 2000 razy potężniejsze niż bomba, która zrównała z Ziemią Hiroshimę, wszystko skoncentrowane w jednym skalnym pocisku mierzącym od 130 do 290 metrów. Ale energia to tylko część historii. Najważniejsze jest to, w jaki sposób ta energia jest dostarczana na powierzchnię naszej planety. A to zależy całkowicie od złożonego tańca fizyki obejmującego kąt wejścia w atmosferę, skład obiektu i czyste kosmiczne szczęście. Różnica między katastrofą regionalną a globalnym wydarzeniem wymierania często sprowadza się do czynników tak prostych, jak to, czy nadlatujący obiekt jest wykonany z litego żelaza czy luźnego żwiru, czy dociera pod ostrym kątem, czy ociera się o atmosferę i czy eksploduje w powietrzu, czy uderza w Ziemię. Prędkość zbliżania FA-22 wynosząca około 10,8 km na sekundę była typowa dla obiektów bliskich Ziemi, wystarczająco szybka, aby sprężyć i ogrzać atmosferę przed sobą w osłonę plazmy, ale nie tak ekstremalna, aby sugerować pochodzenie z zewnętrznego Układu Słonecznego lub dalej. Przy tej prędkości wejście w atmosferę byłoby spektakularnie gwałtowne. Obiekt zacząłby świecić jak drugie Słońce, będąc jeszcze setki kilometrów nad powierzchnią. Jego czołowa krawędź osiągałaby temperaturę kilku tysięcy stopni, gdyby taranował przez coraz gęstsze warstwy powietrza. W przypadku asteroidy kamiennej, w zakresie rozmiarów FA-22, najbardziej prawdopodobnym scenariuszem byłby wybuch powietrzny, całkowita eksplozja atmosferyczna występująca gdzieś między 5 a 15 km nad powierzchnią. Tak właśnie stało się w Tunguskiej na Syberii w 1908 roku, kiedy szacowany wybuch powietrzny o mocy 3 do 15 megaton zrównał z Ziemią ponad 2000 km lasu, nie tworząc nigdy krateru. Scenariusz FA-22 byłby znacznie potężniejszy. Wyobraź sobie, że stoisz w odległości 200 km od epicentrum w pogodny poranek. Najpierw pojawiłoby się światłobłysk jaśniejszy niż słońce, widoczny nawet w biały dzień, palący siatkówki i zapalający odzież i roślinność na setkach kilometrów kwadratowych. Impuls termiczny trwałby kilka sekund, wystarczająco długo, aby spowodować oparzenia 3 stopnia na odsłoniętej skórze w odległościach przekraczających 100 km. Potem nadszedłby dźwięk. Fala uderzeniowa ze 100-megatonowego wybuchu powietrznego rozbiłaby okna na obszarze wielkości małego kraju. Fala nadciśnienia zrównałaby większość budynków mieszkalnych w promieniu 50 km od epicentrum i spowodowałaby znaczne uszkodzenia konstrukcyjne w odległościach zbliżonych do 150 km. Nawet dobrze zbudowane konstrukcje betonowe doznałyby poważnych uszkodzeń w wewnętrznej strefie zniszczenia. Ale co gdyby FA-22 była zbudowana z gęstszego materiału lub nadleciała pod płytszym kątem, co pozwoliłoby jej na głębszą penetrację atmosfery przed fragmentacją? Scenariusz krateru przedstawia zupełnie inny rodzaj zniszczenia. Korzystając z ustalonych programów modelowania uderzeń, takich jak Impact Earth, możemy oszacować, że 200-metrowa żelazna asteroida uderzająca z prędkością 10 km na sekundę wykopałaby krater o średnicy około 3 km i głębokości 500 metrów. Bezpośrednie skutki byłyby apokaliptyczne dla każdego w zasięgu wzroku. Uderzenie wyparowałoby asteroidę i równoważną masę skały, wyrzucając miliony ton przegrzanego gruzu po trajektoriach balistycznych, które zrzuciłyby płonący materiał na tysiące kilometrów kwadratowych. Wstrząs sejsmiczny zarejestrowałby się jako trzęsienie ziemi o magnitudzie 6,5, powodując zawalenie się budynków i wywołując osuwiska na obszarze setek kilometrów. Jednak być może najbardziej przerażającym scenariuszem byłoby uderzenie w ocean. Ponad 70% powierzchni Ziemi jest pokryte wodą, co statystycznie czyni to najbardziej prawdopodobnym wynikiem dla każdej losowo nadlatującej asteroidy. Kiedy kosmiczne pociski uderzają w ocean, nie po prostu znikają w głębinach z dużym pluskiem. Tworzą coś znacznie bardziej niebezpiecznego tsunami. Fizyka tsunami wywołanych uderzeniem jest nadal udoskonalana przez badaczy, ale ostatnie modelowanie sugeruje, że nawet 250-metrowa asteroida uderzająca w głęboki ocean wytworzyłaby początkowe fale o wysokości przekraczającej 100 metrów w miejscu uderzenia. Te fale rozchodziłyby się na zewnątrz z prędkościami samolotów odrzutowych, niosąc wystarczającą energię, aby pozostać niebezpieczne w całych basenach oceanicznych. Uderzenie FA-22 w środkowym Atlantyku mogłoby potencjalnie spowodować, że fale o wysokości 10 metrów rozbijałyby się o miasta przybrzeżne od Bostonu do Barcelony w ciągu kilku godzin od uderzenia. Istnieje jednak ważne zastrzeżenie, które często ginie w scenariuszach katastrof. Wysokość fal zmniejsza się wraz z odległością. Klasyczne symulacje hydrokodu pokazują, że fale tsunami tracą energię podczas podróży, a typowe redukcje wysokości następują zgodnie z przewidywalnymi wzorami matematycznymi. Niszczycielska fala o wysokości 100 metrów w miejscu uderzenia może zostać zredukowana do 10 metrów, zanim pokona 60 km i będzie dalej zmniejszać się, gdy będzie przemierzać baseny oceaniczne. Diabeł jak zawsze tkwi w szczegółach geografii wybrzeża i lokalnej batymetrii. Pytanie o wpływ regionalny kontra globalny jest kluczowe dla zrozumienia prawdziwego zagrożenia stwarzanego przez asteroidy o rozmiarach zabójców miast. Uderzenie FA-22 z pewnością spowodowałoby zniszczenia regionalne potencjalnie dotykające miliony ludzi, ale mało prawdopodobne byłoby wywołanie globalnych zmian klimatycznych lub zagrożenie cywilizacji ludzkiej jako całości. Taki poziom zniszczeń wymaga znacznie większych impaktorów, obiektów o rozmiarach przekraczających kilometr, które uderzają być może raz na kilkaset tysięcy lat. Dla porównania rozważmy wydarzenie w Czelabińsku 15 lutego 2013 roku. Ta 20-metrowa asteroida wywołała wybuch powietrzny o mocy około 500 kiloton TNT. Zraniła ponad 1500 osób, głównie latającym szkłem z rozbitych okien, i dostarczyła światu dramatyczne nagrania z kamer samochodowych, pokazujące, co dzieje się, gdy kosmiczne szczątki spotykają się z nowoczesną cywilizacją. Obiekt czelabiński miał mniej więcej 1/10 średnicy FA-22, co pokazuje, jak szybko energia uderzenia skaluje się wraz z rozmiarem. Co szczególnie zaniepokoiło ekspertów do spraw obrony planetarnej w Czelabińsku, to nie spowodowane przez niego zniszczenia, ale fakt, że dotarł on całkowicie niezauważony. Asteroida zbliżała się od strony Słońca, ukryta w słonecznym blasku, aż do ostatnich chwil przed wejściem w atmosferę. Żaden teleskop na Ziemi jej nie widział. Reprezentuje to jedną z fundamentalnych ślepych plamek w naszej obecnej sieci wykrywania korytarz zbliżania się od strony Słońca, gdzie nawet obiekty wielkości zabójcy miast mogą dotrzeć praktycznie bez ostrzeżenia. Bezpieczny przelot FA-22 w rzeczywistości dostarczył cennego, rzeczywistego doświadczenia dla międzynarodowej koordynacji obrony planetarnej. Krótkie pojawienie się asteroidy na liście oceny ryzyka Europejskiej Agencji Kosmicznej, a następnie jej usunięcie po dodatkowych obserwacjach, które doprecyzowały orbitę, dało agencjom praktykę w delikatnej sztuce komunikacji publicznej na temat potencjalnie niebezpiecznych obiektów. Jak informować społeczeństwo o możliwym zagrożeniu, nie wywołując paniki, jak koordynować międzynarodowe działania w przypadku obiektów, które mogą dotknąć wielu krajów. Międzynarodowa sieć ostrzegawcza Asteroid przeprowadziła coś, co można nazwać ćwiczeniem na żywo podczas zbliżania się FA-22, testując protokoły komunikacyjne i procedury koordynacji obserwacji, które byłyby kluczowe w prawdziwym nagłym wypadku. Fakt, że ostatecznie był to fałszywy alarm, nie zmniejszył wartości doświadczenia. W rzeczywistości dostarczył coś jeszcze cenniejszego – dowód, że system może działać pod presją. Ale ćwiczenie to również uwydatniło krytyczne luki, które nadal istnieją w naszych możliwościach obrony planetarnej. Czas wyprzedzenia jest wszystkim, jeśli chodzi o odchylenie asteroidy. Im wcześniej wykryjemy potencjalnie niebezpieczny obiekt, tym mniejsze odchylenie jest potrzebne do bezpiecznej zmiany jego trajektorii. Delikatne pchnięcie zastosowane z wieloletnim wyprzedzeniem może wyeliminować potrzebę desperackich działań w ostatniej chwili. Obecne technologie odchylenia, zatwierdzone przez udaną misję DART NASA, opierają się głównie na uderzeniu kinetycznym, zasadniczo grając w kosmicznego bilarda z asteroidami za pomocą szybkich statków kosmicznych. Technika działa, ale wymaga precyzyjnej wiedzy o składzie, strukturze i stanie rotacji celu. Asteroida typu kupa gruzu reaguje na uderzenie bardzo inaczej niż solidna żelazna góra, a popełnienie błędu w tych obliczeniach może oznaczać różnicę między udanym odchyleniem a katastrofalną fragmentacją. Scenariusz FA-22 służy jako otrzeźwiające przypomnienie, że żyjemy na planecie osadzonej w strzelnicy kosmicznych szczątków. Większość z nich to nieszkodliwe cząstki o rozmiarach ziaren piasku, które nieszkodliwie spalają się w naszej atmosferze jako deszcze meteorów, ale czasami coś większego prześlizguje się przez luki w naszej sieci wykrywania. A kiedy tak się dzieje, konsekwencje mogą być niszczycielskie w skalach od bloków miejskich po całe cywilizacje. Dobrą wiadomością jest to, że coraz lepiej radzimy sobie z tą kosmiczną strażą sąsiedzką. Nowe teleskopy obserwacyjne wchodzą do użytku z bezprecedensową zdolnością wykrywania i śledzenia potencjalnie niebezpiecznych obiektów, podczas gdy kosmiczne obserwatoria podczerwone wkrótce zamkną lukę w wykrywaniu od strony Słońca, która pozwoliła Czelabińskowi pojawić się bez ostrzeżenia. Jednak w miarę jak staliśmy się bardziej biegli w katalogowaniu zagrożeń w naszym bezpośrednim sąsiedztwie Układu Słonecznego, zaczęliśmy również zdawać sobie sprawę, jak wiele jeszcze nie wiemy o szerszym środowisku kosmicznym. Obiekty takie jak 3P Atlas przypominają nam, że nasz Układ Słoneczny nie jest odizolowaną wyspą, ale raczej przystankiem na galaktycznej autostradzie, stale przyjmującym gości z ogromnych przestrzeni międzygwiezdnych, co rodzi intrygujące pytanie o wrześniowy przypływ. Czy byliśmy świadkami losowego zgrupowania niepowiązanych obiektów, czy też mogły istnieć głębsze powiązania między FA-22, innymi asteroidami bliskimi Ziemi i tajemniczym międzygwiezdnym gościem, który zdominował astronomiczne nagłówki? Zanim będziemy mogli odpowiedzieć na to pytanie, musimy zrozumieć, co jeszcze dzieliło kosmiczną scenę w tych niezwykłych jesiennych tygodniach. Część trzecia. Łabędź Apofis i fala komet. Podczas gdy asteroida FA-22 zdominowała nagłówki swoim bliskim przelotem, inny kosmiczny wykonawca cicho przygotowywał się do swojego debiutu na wieczornym niebie. Kometa C-2025R2, odkryta przez instrument SWAN do badania anizotropii wiatru słonecznego na pokładzie statku kosmicznego SOHO 11 września, szybko jaśniała, zbliżając się do widzialności gołym okiem, gdy zbliżała się do Słońca. W przeciwieństwie do przewidywalnej i dobrze zmapowanej trajektorii FA-22, Ta kometa reprezentowała coś znacznie bardziej zmiennego i nieprzewidywalnego. Odkrycie komety przez Swan uwydatniło jeden z najbardziej eleganckich aspektów nowoczesnej astronomii kosmicznej. Instrument nie został zaprojektowany do polowania na komety. Jego główna misja obejmuje mapowanie emisji wodoru z interakcji wiatru słonecznego na granicy naszego Układu Słonecznego. Okazuje się jednak, że gdy komety rozpoczynają swoje ostateczne zbliżanie się do Słońca, zaczynają uwalniać bogatą w wodór parę wodną w ilościach wykrywalnych z milionów kilometrów. Swan w zasadzie natrafia na nowe komety, obserwując ich sygnatury wodorowe, wybuchające na tle przestrzeni międzyplanetarnej. W połowie września C2025 R2 pojaśniała do około 6 wielkości, unosząc się tuż na granicy widzialności gołym okiem pod ciemnym wiejskim niebem. Astronomowie amatorzy zaczęli zgłaszać obserwacje w pobliżu konstelacji Panny blisko jasnej gwiazdy Spica i czerwonawego blasku Marsa na zachodnim niebie po zachodzie Słońca. Warkocz komety stawał się coraz dłuższy i bardziej ustrukturyzowany, ponieważ ogrzewanie słoneczne powodowało sublimację lotnych ludów z jej jądra, tworząc klasyczną komę i strukturę warkocza, która inspirowała ludzką wyobraźnię przez tysiąclecia. Ale komety to notorycznie kruche stworzenia. W przeciwieństwie do solidnej skały i metalowej konstrukcji, asteroid komety są w zasadzie brudnymi śnieżkami, luźnymi skupiskami lodu, pyłu i związków organicznych, utrzymywanych razem przez słabe siły grawitacyjne i zamarznięte substancje lotne. Gdy zbliżają się do Słońca, to samo ogrzewanie, które tworzy ich spektakularne warkocze, może również całkowicie je rozerwać. Wiele komet odkrytych przez Swan nigdy nie przeżywa swojego pierwszego bliskiego spotkania z promieniowaniem słonecznym, fragmentując się w strumienie gruzu, które wytwarzają krótkie deszcze meteorów, zanim całkowicie się rozproszą. Fizyka aktywacji komety obejmuje złożoną interakcję temperatur, sublimacji i ogrzewania słonecznego. Lód wodny zaczyna sublimować w temperaturach około 200 stopni Kelwina, podczas gdy bardziej lotne związki, takie jak dwutlenek węgla i metan, zaczynają odgazowywać się w jeszcze większych odległościach od Słońca. Gdy te materiały przechodzą bezpośrednio ze stanu stałego w gazowy, tworzą strumienie gazu, które mogą dramatycznie zmieniać trajektorię komety poprzez siły niegrawitacyjne. To sprawia, że orbity komet są notorycznie trudne do przewidzenia z dużą precyzją, szczególnie w przypadku obiektów wykonujących swoje pierwsze zbliżenie z odległego obłoku Oorta C2025. Szanse na przetrwanie R2 pozostawały niepewne przez cały wrzesień. Świeże komety z zewnętrznego Układu Słonecznego często zawierają pierwotne lody, które nigdy nie były narażone na znaczne ogrzewanie słoneczne. Kiedy w końcu napotykają promieniowanie słoneczne, szybka sublimacja może stworzyć wewnętrzne naprężenia, które przekraczają integralność strukturalną komety. Jądro może rozpaść się na wiele fragmentów, z których każdy tworzy własny warkocz, i komę lub może całkowicie rozpaść się w rozszerzającą się chmurę gruzu. Jednak nawet gdy ta nowa kometa przyciągała uwagę obserwatorów amatorów, inna kosmiczna gwiazda przygotowywała się na swój własny moment w centrum uwagi. Asteroida 99942, Apophis, 400-metrowa góra skał, która kiedyś znajdowała się na szczycie każdej listy obaw dotyczących obrony planetarnej, kontynuuje swoje niepowstrzymane zbliżanie się do najbliższego spotkania asteroid w historii ludzkości. 13 kwietnia 2029 roku Apophis przeleci obok Ziemi w odległości zaledwie 32 000 km bliżej niż nasze satelity geostacjonarne, wystarczająco blisko, aby pojawić się jako jasna, szybko poruszająca się gwiazda, widoczna gołym okiem nawet z obszarów miejskich. Przelot nastąpi z prędkością około 50 000 km na godzinę, co oznacza, że obserwatorzy będą mogli obserwować ruch asteroidy na tle pola gwiazd w czasie rzeczywistym bez teleskopów. To, co sprawia, że spotkanie z Apophisem jest fascynujące naukowo, to fakt, że z absolutną pewnością wiemy, że nie stanowi ono żadnego ryzyka uderzenia przez co najmniej następne stulecie. Obserwacje radarowe i optyczne śledzenie dopracowały jego orbitę z niezwykłą precyzją, eliminując wszelką możliwość kolizji podczas przelotu w 2029 roku lub przez dziesięciolecia później. Pozwala to naukowcom skupić się wyłącznie na niezwykłej okazji do badania dużej asteroidy podczas ekstremalnie bliskiego przelotu. Grawitacyjne efekty przyciągania Ziemi podczas przelotu będą głębokie i trwałe. Apofiz doświadczy sił pływowych wystarczająco silnych, aby zmienić jej prędkość obrotową, zmodyfikować jej cechy powierzchniowe i potencjalnie wywołać osuwiska lub redystrybucję regolitu na całej jej powierzchni. Asteroida, która wyłoni się ze spotkania, będzie mierzalnie różniła się od tej, która się zbliżyła, stanowiąc naturalne laboratorium do badania, w jaki sposób bliskie spotkania planetarne przekształcają małe ciała w czasie geologicznym. Misja OSIRIS-APEX NASA, zmieniona wersja udanej misji powrotnej próbek OSIRIS-REx jest już w drodze, aby spotkać się z Apofisem wkrótce po przelocie w 2029 roku. Statek kosmiczny spędzi miesiące na mapowaniu powierzchni asteroidy po spotkaniu, mierząc, jak interakcja grawitacyjna z Ziemią zmieniła jej właściwości fizyczne i wewnętrzną strukturę. Te dane będą bezcenne dla przyszłych misji odchylania asteroid, które muszą uwzględniać, jak obiekty docelowe reagują na siły zewnętrzne. Czas zbliżania się Apofis zaledwie 3,5 roku po wrześniowym przypływie w 2025 roku rodzi intrygujące pytania, czy wchodzimy w okres zwiększonej aktywności obiektów bliskich Ziemi. Statystycznie rzecz biorąc, bliskie zbliżenia asteroid nie podlegają żadnemu szczególnemu harmonogramowi. Są to w zasadzie losowe zdarzenia, rządzone złożonymi interakcjami grawitacyjnymi, które kształtują Układ Słoneczny przez miliardy lat. Jednak zgrupowanie znaczących spotkań w tak krótkim czasie wydaje się podważać pojęcie czysto losowego rozkładu. Część tego pozornego wzrostu wynika z błędu obserwacyjnego. Zakończenie głównych badań asteroid, takich jak Linear NEAT i Spacewatch, w ciągu ostatnich 2 dekad znacznie poprawiło naszą zdolność do wykrywania i śledzenia potencjalnie niebezpiecznych obiektów. Obserwatorium Vera C. Rubin, które uchwyciło swoje pierwsze obrazy świetlne w czerwcu 2025 roku, stanowi kolejny skok kwantowy w możliwościach badań. Jego ogromne pole widzenia i czułe detektory co kilka nocy ponownie skanują całe dostępne niebo, zapewniając bezprecedensową częstość odkrywania nowych obiektów i monitorowania znanych. Ale same ulepszone możliwości wykrywania nie wyjaśniają wrześniowego przypływu ani niezwykłej różnorodności zaangażowanych obiektów. Obok bliskiego przelotu FA-22 i jaśniejącego pokazu CETA 2025R2, dziesiątki mniejszych obiektów bliskich Ziemi przecinały naszą lokalną kosmiczną okolicę. Object 2025 RJ2 passed at just 0.78 lunar distances on September 15th. Multiple sublunar distance encounters occurred throughout the month, each one catalogued and tracked by the Global Space Surveillance Network. The seasonal timing might offer clues about the underlying dynamics. Earth's orbital motion carries us through different regions of the inner solar system throughout the year, and it's possible that September 2025 corresponded to our passage through a particularly populated zone of space debris. Alternatively, the apparent clustering might result from the complex gravitational resonances that can synchronize the orbits of multiple objects over geological time scales. Comets add another layer of complexity to this cosmic choreography. Unlike asteroids, which follow relatively stable and predictable orbits, comets can experience dramatic changes in trajectory due to outgassing forces and gravitational perturbations from the giant planets. Long-period comets from the Oort cloud arrive with essentially no advanced warning, following orbits that haven't brought them into the inner solar system for thousands or millions of years. The distinction between asteroids, comets, and meteors often confuses public discussions of planetary defense. Yet these differences are crucial for understanding impact risks and mitigation strategies. Asteroids are essentially rocky or metallic mountains in space, following well-defined orbits that change slowly over time. Comets are volatile rich objects whose behavior can be unpredictable due to outgassing effects. Meteors are simply the visible light phenomena created when small particles burn up in Earth's atmosphere, regardless of whether their parent body was an asteroid or comet. This diversity of small body types reflects the complex history of our solar system's formation and evolution. The asteroid belt between Mars and Jupiter contains remnants of planetary formation that never successfully assembled into a planet, while comets preserve samples of the primitive ices and organics from the outer reaches of the early solar nebula. Each population tells part of the story of how worlds form around stars, and each presents different challenges for planetary defense. As autumn 2025 progressed, the cosmic stage was set for even more remarkable revelations. The September surge of familiar solar system objects was about to be overshadowed by something unprecedented, a visitor from another star system entirely carrying chemical signatures that would challenge fundamental assumptions about planetary formation and the nature of interstellar space. But first, this mysterious traveler would have to navigate the complex gravitational environment of our inner solar system, while remaining hidden behind the solar glare during its closest approach to the Sun's location. When it finally emerged into telescopic view in early December, 3, Atlas would prove to be unlike anything astronomers had ever seen before. Part 4, The Interstellar Intruder. On July 1, 2025, a routine automated sky survey captured something extraordinary disguised as an unremarkable dot of light. The Atlas telescope array at Riohacha, Chile, had photographed thousands of such objects, asteroids, comets, and distant stars shifting position against the stellar background. But this particular dot would soon rewrite our understanding of what travels between the stars. Initially catalogued as just another potential near-Earth object, the object that would become known as 3I Atlas appeared no different from countless other discoveries in the Atlas database. The automated systems flagged it for follow-up observations based on its apparent motion across the sky, and within days telescopes around the world were tracking its trajectory with increasing precision. It was during this routine astrometric follow-up that astronomers realized they were dealing with something unprecedented. The mathematics were unmistakable. As more observational data refined the object's orbital elements, one parameter stood out with startling clarity. Its orbital eccentricity exceeded unity. In celestial mechanics, this is the signature of a hyperbolic trajectory, an orbit carrying more than enough velocity to escape the Sun's gravitational influence entirely. This object wasn't bound to our solar system. It was just passing through. 3I Atlas became only the third confirmed interstellar visitor in human history, following the mysterious cigar-shaped object 1I Oumuamua in 2017 and comet 2I Borisov in 2019. But unlike those previous visitors, 3I Atlas arrived with perfect timing for extensive observation. Its trajectory would carry it to perihelion's closest approach to the Sun on approximately October 30th, 2025, followed by its closest approach to Earth in December at a distance of roughly 1.8 astronomical units. That December distance translates to approximately 270 million kilometers, far enough to pose absolutely zero threat to Earth, but close enough for detailed spectroscopic analysis by our most powerful telescopes. It was as if the cosmos had arranged a cosmic delivery service, dropping off a pristine sample from another star system with optimal viewing conditions and plenty of advance notice. But the object's trajectory was only the beginning of its mysteries. As observational data accumulated throughout the summer and early autumn of 2025, 3I Atlas began displaying characteristics that challenged assumptions about both interstellar space and comet behavior. Size estimates from Hubble Space Telescope observations suggested an upper limit of approximately 5.6 kilometers for the nucleus, though the actual size was likely significantly smaller. This placed it in the intermediate range between typical comet nuclei and small asteroids. What truly set 3 Atlas apart from its interstellar predecessors was its unmistakably cometary behavior. Unlike 1I Oumuamua, which showed no visible coma or tail, despite its puzzling non-gravitational acceleration, 3I Atlas developed a classic cometary appearance as it approached the Sun's position. By September, ground-based telescopes were resolving a substantial coma, the cloud of dust and gas surrounding the nucleus, along with the beginnings of what would become an impressive tail structure. This cometary activity provided the first clues to the object's truly alien chemistry. When the James Webb Space Telescope turned its infrared spectrographs toward 3I Atlas in late summer 2025, the results were unlike anything seen in solar system comets. The object's coma showed an unusually high ratio of carbon dioxide to water vapor, among the highest CO2 to H2O ratios ever measured in a comet. To understand why this chemistry is so significant, consider how comets typically form in planetary systems. Water ice condenses from the protoplanetary nebula at temperatures around 150 Kelvin, corresponding to orbital distances of approximately 2 to 3 astronomical units from a Sun-like star. This is why most solar system comets, which formed in the outer regions beyond Neptune's orbit, still contain substantial quantities of water ice mixed with other volatiles. Carbon dioxide, with its lower sublimation temperature, only becomes a major component of cometary ices at distances exceeding 10 astronomical units from the parent star, where temperatures drop below 80 Kelvin. Even then, CO2 typically remains a minor constituent compared to water ice. The extreme carbon dioxide dominance in 3I Atlas suggests either formation under conditions unlike anything in our solar system, or subsequent processing that selectively depleted water while preserving CO2. One possibility involves formation in the frigid outer regions of a planetary system much larger or colder than our own. If 3I Atlas condensed from a protoplanetary disk around a low-mass star, or in the distant reaches of a system with multiple giant planets, it might have formed in a zone where carbon dioxide ice was the primary volatile constituent. In such environments, water might never have condensed in significant quantities, leading to the extreme composition ratios observed by JWST. Alternatively, the object might have undergone extensive processing during its long journey through interstellar space. Cosmic ray bombardment over millions or billions of years could potentially alter surface chemistry through radiolysis, the breaking of chemical bonds by high-energy radiation. If this process preferentially removed water molecules while leaving carbon dioxide intact, it might explain the current composition without requiring exotic formation conditions. But the chemical anomalies didn't stop with carbon dioxide dominance. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent nickel emission lines with surprisingly weak corresponding signatures from iron. This represents a significant departure from typical solar system compositions, where iron and nickel occur in roughly solar proportions, reflecting the elemental abundances of the stellar nebula from which they condensed. The apparent depletion of iron relative to nickel in 3I Atlas raises fundamental questions about its formation, environment, or subsequent evolution. One speculative possibility involves differential processing of metallic components during the object's interstellar journey. Iron and nickel have different sublimation temperatures and chemical reactivities, so prolonged exposure to cosmic radiation or interstellar dust impacts might selectively remove iron while preserving nickel in more stable chemical forms. Another intriguing hypothesis involves the possibility that 3 Atlas formed in a stellar environment with non-solar elemental abundances. If its parent star belonged to a different galactic population, perhaps the thick disk or halo components that contain stars with unusual chemical compositions, The resulting planetary debris might naturally exhibit iron to nickel ratios, unlike those seen in our local cosmic neighborhood. As summer turned to autumn and 3, I Atlas approached its October perihelion, its tail structure became increasingly complex and visually spectacular. Ground-based observations from facilities like the Gemini Observatory documented multiple tail components with different orientations, colors, and apparent particle sizes. This multi-component structure suggested ongoing activation of different volatile reservoirs across various regions of the nucleus. The object was literally coming alive under solar heating after potentially billions of years in the cold emptiness between stars. The timeline for observing 3I Atlas presented both opportunities and challenges. As it approached perihelion in late October, the comet would become increasingly difficult to observe from Earth due to its proximity to the Sun in our sky. Solar glare would effectively hide the object during its most active phase, when thermal processing might reveal additional clues about its composition and internal structure. But patience would be rewarded. Earth's orbital motion would gradually improve the viewing geometry throughout November, and by early December 3, I Atlas would emerge from behind the solar glare into prime observing position. At closest approach to Earth in mid-December, the object would still be nearly 200 times farther away than the Moon, but well positioned for extended spectroscopic campaigns by major observatories. The intervening months of hidden observation presented a tantalizing mystery. What changes would occur as 3I Atlas reached peak solar heating? Would its unusual chemistry remain stable, or would the intense radiation drive off surface materials to reveal different compositions beneath? Most importantly, would the object survive perihelion intact, or would thermal stresses fragment it into multiple pieces? Like so many comets before it, preliminary kinematic modeling suggested that 3I Atlas might be extraordinarily old, possibly more than 7 billion years, if recent calculations linking it to the galaxy's thick disk population proved correct. This would make it older than our entire solar system, a wanderer that had been drifting through interstellar space since before Earth existed. The chemical signatures preserved in its ices and rocky components could provide direct samples of conditions in the early galaxy when star formation rates and heavy element abundances were dramatically different from today. Unlike 1I Oumuamua's brief visit and rapid departure, 3I Atlas offered the prospect of extended study across multiple observing seasons. Its moderate approach, velocity, and favorable geometry would keep it within range of major telescopes well into 2026, providing unprecedented opportunity to characterize an authentic piece of another star system. But even as astronomers prepared for months of detailed observations, nagging questions remained about the object's origins and journey to our solar system. How long had it been wandering in interstellar space? What star system had ejected it, and under what circumstances? Most intriguingly was its arrival during the same period as the September asteroid surge purely coincidental, or could there be deeper connections between the interstellar visitor and the unusual clustering of near-Earth object encounters? The apparent synchronization of cosmic events was beginning to strain credibility. First the parade of close-approaching asteroids, then the brightening comet, and finally the emergence of an interstellar visitor with unprecedented chemical signatures. Either we were witnessing an extraordinarily unlikely convergence of unrelated phenomena, or something more fundamental was orchestrating this celestial performance. As 3 Atlas continued its descent toward perihelion, hidden behind the growing solar glare, astronomers could only speculate about what revelations awaited its December re-emergence. But already the object had begun to reveal secrets that would reshape our understanding of planetary formation, interstellar chemistry, and our place in the galactic community. The question was no longer whether this visitor would provide new insights into the cosmos. It was whether we were prepared for the implications of what it might reveal about the universe beyond our solar system's boundaries. The real mystery, however, was only beginning to unfold. Because while 3I Atlas dominated scientific attention with its alien chemistry and ancient origins, a growing number of researchers were starting to notice patterns in the September surge that suggested something more than random cosmic coincidence was at work. Part 5, Planetary Defense Wake-Up Call. The September 2025 surge served as an uncomfortable reminder of just how precarious our planetary defense capabilities remain, despite decades of technological advancement and international cooperation. While we successfully tracked and characterized every significant object that approached Earth during those eventful weeks, the clustering of encounters highlighted critical gaps that could prove catastrophic if filled by the wrong kind of visitor at the wrong time. Consider the fundamental challenge of detection geometry. The vast majority of our asteroid hunting telescopes are ground-based facilities that can only observe objects when they're sufficiently separated from the Sun in our sky. This creates a massive blind spot in the direction of our nearest star, precisely the approach corridor that delivered the Chelyabinsk impactor, completely undetected in 2013. An asteroid approaching from the sunward direction remains effectively invisible until the final hours or minutes before atmospheric entry. FA-22's trajectory fortunately carried it well clear of this detection shadow, allowing telescopes worldwide to track its approach for weeks before closest passage. But if its orbit had been inclined differently, or if its approach vector had aligned more closely with the Sun-Earth line, we might have had mere days or hours of warning instead of the comfortable lead time that allowed detailed characterization and public notification. This sunward blind spot represents one of the most significant vulnerabilities in our current planetary defense architecture. Ground-based surveys have made remarkable progress in cataloging near-Earth objects, but they remain fundamentally limited by the laws of optics and orbital mechanics. You cannot observe what is hidden behind the brightest object in the sky, no matter how sophisticated your telescope. The solution involves moving detection systems into space, where they can operate independent of Earth's daylight cycle and atmospheric interference. NASA's Near-Earth Object Surveyor mission, scheduled for launch in September 2027, will deploy an infrared space telescope specifically designed to hunt asteroids from a position trailing Earth in our orbit around the Sun's location. From this vantage point, NEO Surveyor will be able to detect objects approaching from directions that remain invisible to ground-based observatories. But space-based detection is only the first step in a complex chain of planetary defense capabilities. Once a potentially hazardous object is discovered, it must be characterized in sufficient detail to assess the actual threat level and determine the most effective response strategy. This requires rapid follow-up observations from multiple facilities, precise orbit determination, and detailed analysis of the object's physical properties. The Vera C. Rubin Observatory, which captured its first light images in June 2025, represents a revolutionary advancement in this follow-up capability. Its enormous mirror and wide-field camera can rescan the entire accessible sky every 3 nights, providing unprecedented cadence for tracking newly discovered objects and monitoring their orbital evolution. In its first 10 hours of operation, Rubin netted thousands of new asteroid detections, demonstrating the instrument's potential to dramatically expand our census of the near-Earth object population. Yet detection and tracking are meaningless without the ability to actually do something about incoming threats. This is where NASA's Double Asteroid Redirection Test Mission has provided invaluable real-world validation of kinetic deflection technology. The DART spacecraft's impact with asteroid Dimorphos on September 26, 2022, successfully altered the small asteroid's orbital period by 32 minutes, far exceeding the minimum 4-minute change required to confirm mission success. More importantly, detailed analysis of the impact revealed that the momentum transfer efficiency, known as beta, was approximately 3.6, meaning the impact was nearly 4 times more effective than would be predicted by simple momentum conservation. This enhancement factor results from the ejection of debris following impact, which acts like a rocket exhaust to amplify the deflection effect. Understanding this physics is crucial for designing future deflection missions. The European Space Agency's Hera mission, currently en route to the Didymos system, will arrive in 2026 to conduct forensic analysis of the DART impact site. Hera's detailed mapping and measurement of the crater and debris field will provide ground truth data for impact models, helping refine our understanding of how different asteroid types respond to kinetic deflection attempts. But kinetic impact is just one tool in the planetary defense toolkit. For larger objects or scenarios requiring more precise trajectory changes, other techniques might prove more effective. Gravity tractors, spacecraft that use their own gravitational field to gently tug asteroids off course. Velocity changes accumulated over years or decades. Nuclear standoff devices could vaporize surface material to create powerful rocket-like thrust. Ion beam shepherds could use focused particle beams to gradually ablate one side of an asteroid, creating continuous, low-level thrust over extended periods. The key insight from planetary defense research is that all of these techniques require substantial lead time to be effective. A gentle nudge applied years or decades in advance can eliminate the need for desperate last-minute measures. This is why early detection is so critical. Not because we need time to evacuate cities or build underground shelters, but because gentle deflection becomes exponentially easier with advanced warning. The International Asteroid Warning Network, established to coordinate global response to potential impact threats, conducted what amounted to a live exercise during FA-22's approach. The asteroid's brief appearance on the European Space Agency's risk assessment list, followed by its removal after additional observations, provided valuable experience in the delicate balance between public notification and panic prevention. How do you inform the world about a possible asteroid threat without causing economic chaos or social disruption? How do you coordinate international response efforts when dealing with objects that could affect multiple countries? These questions have no easy answers, but FA-22's flyby provided a relatively low-stakes opportunity to test communication protocols and decision-making processes. The exercise revealed both strengths and weaknesses in our current approach. The rapid international sharing of observational data allowed quick refinement of FA-22's orbit and prompt removal from risk assessment lists once the threat was ruled out. But public communication remained inconsistent, with some media outlets sensationalizing the initial risk assessment, while others ignored the story entirely until after the safe flyby was confirmed. Part of this communication challenge stems from the inherent uncertainty in early orbital determinations. When an asteroid is first discovered, its trajectory is poorly constrained due to limited observational data. The uncertainty region, the range of possible orbits consistent with available measurements, can include both impact and miss scenarios. Only additional observations can narrow this uncertainty enough to make definitive predictions. This creates a fundamental tension in planetary defense communication. Waiting until impact probability drops to zero means potentially losing valuable preparation time if the object does turn out to be on a collision course. But releasing information while significant uncertainty remains risks triggering unnecessary panic or worse, public skepticism if the threat assessment changes as better data becomes available. The September surge also highlighted gaps that remain in our detection capabilities despite recent advances. Long-period comets arriving from the outer solar system can still appear with relatively little warning, as their highly elliptical orbits spend most of their time in the distant reaches where they remain undetectable. Comet Swift-Tuttle, for example, won't return to the inner solar system until 2026, but its nucleus is estimated at 26 kilometers in diameter, large enough to cause global devastation if its orbit were to intersect Earth's path. Perhaps most concerning are the city-killer-sized objects in the 100 to 300 meter range, large enough to cause regional devastation, but small enough to remain difficult to detect until they're very close to Earth. Current surveys have catalogued most of the kilometer-plus objects capable of causing global effects, but the inventory of smaller potentially hazardous asteroids remains incomplete. The September events also raised uncomfortable questions about our ability to handle multiple simultaneous threats. While FA-22 dominated headlines, dozens of smaller objects were simultaneously threading their way through our local cosmic neighborhood. If several city-killer-sized asteroids were approaching simultaneously from different directions, would our tracking and characterization capabilities be overwhelmed? Could we mount deflection missions against multiple targets using current technology and resources? These scenarios remain hypothetical, but they highlight the importance of continued investment in planetary defense infrastructure. The completion of the Rubin Observatory survey, the deployment of NEO surveyor, and the ongoing development of deflection technologies represent crucial steps toward a truly robust planetary defense capability. But they also represent just the beginning of what will be a multi-generational effort to safeguard human civilization against cosmic impacts. The good news is that planetary defense is fundamentally a solvable problem. Unlike earthquakes, volcanic eruptions, or other natural disasters, asteroid impacts can be prevented entirely with sufficient advanced warning and appropriate technology. The physics of deflection are well understood. The necessary technologies are within our current capabilities, and the international cooperation framework already exists. What we need now is the political will to maintain funding and support for these systems during the long intervals between major impact threats. Planetary defense is like insurance. It seems unnecessary right up until the moment you desperately need it. The September surge served as a valuable reminder that we live in an active cosmic environment, where impacts are not a matter of if but when. Yet as astronomers work to catalog and characterize the parade of near-Earth objects during those eventful autumn weeks, a different kind of mystery was beginning to emerge from the observational data. The timing of the encounters, the clustering of trajectories, and the remarkable coincidence of an interstellar visitor arriving during the same narrow window was starting to strain the limits of statistical probability. Were we witnessing an extraordinarily unlikely convergence of unrelated events, or was something more fundamental orchestrating this cosmic choreography? Part 6. What is following 3 Atlas? The human brain is exquisitely designed to detect patterns even when none exist. This evolutionary adaptation helped our ancestors identify predators hiding in tall grass and recognize seasonal changes that meant the difference between feast and famine. But in the context of astronomical phenomena, this same pattern recognition system can lead us astray, finding connections and conspiracies in the random noise of cosmic events. Yet sometimes the patterns are real. Consider the timeline. Asteroid 2025 FA-22 sweeps past Earth on September 18th at 2.2 lunar distances. 3 days earlier, smaller object 2025 RJ2 passes at just 0.78 lunar distances. Throughout the same week, multiple additional near-Earth objects thread their way through our local cosmic neighborhood, each one catalogued and tracked by global surveillance networks. Comet C 2025 R2 brightens toward naked eye visibility in the evening sky, and lurking in the background interstellar visitor 3, I-Atlas approaches its October perihelion after a journey that may have lasted billions of years. Taken individually, none of these events is particularly remarkable. Dozens of asteroids pass within 0.05 astronomical units of Earth every month following orbital mechanics established billions of years ago. Comets regularly brighten and fade as they approach and recede from the Sun's orbit. Interstellar objects, while rare, are expected consequences of planetary formation and evolution around other stars. But the clustering of these events within such a narrow temporal window begins to challenge simple explanations based on cosmic coincidence. What are the odds that an interstellar visitor would arrive during the same month as an unusually active period of near-Earth object encounters? How likely is it that a newly discovered comet would reach peak visibility just as multiple asteroids are making close approaches? One speculative thread worth examining involves gravitational shepherding, the possibility that 3I Atlas's passage through the inner solar system could somehow influence the trajectories of smaller objects. Large bodies can gravitationally perturb the orbits of smaller ones, potentially creating a debris stream or entourage effect that might explain the clustering of September encounters. However, the physics argue strongly against this romantic notion. 3I Atlas, even at its maximum estimated size of approximately 6 kilometers, carries insufficient mass to gravitationally influence objects at distances of millions of kilometers. Newton's inverse square law means that gravitational effects fall off rapidly, with distance becoming negligible at the scales involved in the September encounters. To put this in perspective, the gravitational tug between 3I Atlas and asteroid FA22 during their simultaneous presence in the inner solar system would be roughly equivalent to the gravitational attraction between two automobiles parked in neighboring cities. Yet the persistence of gravitational shepherding theories reveals something important about human psychology and our relationship with cosmic phenomena. We instinctively search for causal connections between simultaneous events, even when the underlying physics makes such connections impossible. This tendency served our ancestors well when identifying cause and effect relationships in terrestrial environments, but it can lead us astray when applied to astronomical phenomena operating on scales that dwarf human experience. More exotic cascade scenarios involve possible connections between 3I Atlas and solar activity. Could an interstellar visitor somehow trigger increased solar flaring or coronal mass ejections that might affect space weather around Earth? This idea taps into legitimate concerns about solar-terrestrial interactions and the vulnerability of modern technological civilization to geomagnetic storms. However, the physics of solar dynamics operate on energy scales that make comet-solar interactions essentially irrelevant. The Sun releases approximately 3.8 times 10 to the 26th watts of energy continuously, more power in 1 second than human civilization has consumed throughout all of recorded history. The gravitational and electromagnetic influence of a small interstellar comet at distances exceeding 100 million kilometers would be completely overwhelmed by the much larger forces that drive solar variability. Solar activity follows well-documented cycles related to the Sun's internal magnetic dynamo, not the presence or absence of small visitors in the outer reaches of the solar system. Correlation between comet appearances and solar events occasionally occurs by pure chance, but these coincidences represent statistical noise rather than causal relationships. The meteor shower scenario presents another tempting but ultimately unsupported speculation. Could 3I Atlas be trailing a debris stream that might produce spectacular meteor displays when Earth passes through the material? This idea gains superficial plausibility from the fact that many annual meteor showers result from Earth encountering debris streams left behind by comets. But interstellar meteor streams face fundamental physics problems that make them essentially undetectable from Earth. The debris ejected from 3I Atlas carries the same hyperbolic velocity as the parent object, meaning any particles it sheds will also escape the solar system rather than settling into stable orbits that could intersect Earth's path. By the time our planet reaches the region where 3 Atlas pass through, any ejected material will have dispersed across volumes of space so vast that the particle density becomes negligible. Moreover, the high relative velocities involved in interstellar encounters mean that any debris particles that did somehow encounter Earth would impact our atmosphere at speeds exceeding 70 kilometers per second, much faster than typical solar system meteors. Such high-velocity impacts would produce brief bright flashes rather than the prolonged trails that characterize normal meteor showers. The fragmentation fantasy represents yet another attempt to find hidden connections between 3I Atlas and the September asteroid encounters. Could FA-22 and the other near-Earth objects be fragments of the interstellar visitor broken off during some previous passage through the inner solar system and now following independent orbits that bring them back to Earth's vicinity? This scenario faces insurmountable problems with orbital mechanics and chemical composition. True fragments from 3I Atlas would retain hyperbolic trajectories and interstellar chemistry similar to the parent object. The September asteroids display neither characteristic. Their elliptical orbits and typical carbonaceous or silicate compositions indicate conventional solar system origins with no connection to interstellar material. Perhaps the most mundane explanation is also the most likely. We're witnessing the statistical equivalent of multiple lightning strikes, improbable individual events that occasionally cluster together through pure chance. The universe contains no obligation to distribute cosmic encounters evenly across human time scales. Random processes can and do produce apparent patterns that seem meaningful to pattern-seeking intelligence. The rapid expansion of survey capabilities in the mid-2020s means we're observing this cosmic neighborhood with unprecedented sensitivity and cadence. Previous generations of astronomers might have missed most of the September encounters entirely or detected them as isolated events spread across different news cycles. Our current ability to discover, track, and characterize multiple near-Earth objects simultaneously creates opportunities for apparent clustering that didn't exist during earlier epochs of astronomical observation. Yet even as rational analysis argues for coincidence and observational bias, the nagging sense of orchestrated timing persists. 3. I Atlas's precise arrival during a period of enhanced near-Earth object activity, combined with its unprecedented chemical signatures and ancient origins, suggests that we may be witnessing something more significant than a random convergence of unrelated events. The answer may not emerge until we've had months to study 3I Atlas in detail following its December re-emergence from solar glare. Detailed spectroscopic analysis, precise trajectory measurements, and careful comparison with the September asteroid population might reveal connections that aren't apparent in preliminary observations. But if no such connections emerge, if 3I Atlas proves to be genuinely isolated from the September encounters, then we're left with an even more intriguing possibility. Perhaps the universe is simply more active and interconnected than our Earth-centric perspective typically allows us to appreciate. Maybe what seems like an extraordinary convergence from our limited viewpoint is actually business as usual on galactic scales. The question isn't whether something is following 3I Atlas. The question is whether we're finally developing the observational capability to perceive the true complexity of the cosmic environment we've always inhabited. And if that's the case, then the September surge may be just the beginning of our education about what it means to be citizens of a galaxy where 400 billion stars are constantly exchanging material across the vast expanses of interstellar space. But before we can answer those larger questions, we need to understand why 3I Atlas itself is behaving so strangely. Because as autumn progressed and the interstellar visitor approached its closest encounter with the Sun, the telescopes around the world were documenting activity and chemical signatures unlike anything seen in previous comets, solar system or otherwise. Part 7. Weird behaviors and strange features. As 3I Atlas continued its approach toward October, perihelion telescopes around the world began documenting behaviors that challenged fundamental assumptions about comet physics and interstellar chemistry. What had initially appeared to be a relatively straightforward case of a wandering comet from another star system was revealing layers of complexity that seemed to violate established patterns of how such objects should behave. The most striking anomaly emerged from James Webb Space Telescope observations conducted throughout August and September 2025. JWST's infrared spectrographs detected a coma composition dominated by carbon dioxide to an unprecedented degree, with CO2 to water ratios among the highest ever measured in any comet. This wasn't just unusual. It was borderline impossible according to conventional models of comet formation and evolution. To understand why this chemistry is so remarkable, consider how comets typically form in planetary systems. Water ice condenses from protoplanetary disks at temperatures around 150 Kelvin, corresponding to orbital distances of approximately 2 to 3 astronomical units from Sun-like stars. This is why most solar system comets, which formed in the outer regions beyond Neptune's orbit, still contain substantial quantities of water ice mixed with other volatiles. Carbon dioxide, with its lower sublimation temperature, only becomes a major component of cometary ices at distances exceeding 10 astronomical units from the parent star, where temperatures drop below 80 Kelvin. Even then, CO2 typically remains a minor constituent compared to water ice. The extreme carbon dioxide dominance in 3I Atlas suggests either formation under conditions unlike anything in our solar system, or subsequent processing that selectively depleted water while preserving CO2. One possibility involves formation in the frigid outer regions of a planetary system, much larger or colder than our own. If 3I Atlas condensed from a protoplanetary disk around a low-mass star, or in the distant reaches of a system with multiple giant planets, it might have formed in a zone where carbon dioxide ice was the primary volatile constituent. In such environments, water might never have condensed in significant quantities, leading to the extreme composition ratios observed by JWST. Alternatively, the object might have undergone extensive processing during its long journey through interstellar space. Cosmic ray bombardment over millions or billions of years could potentially alter surface chemistry through radiolysis, the breaking of chemical bonds by high-energy radiation. If this process preferentially removed water molecules while leaving carbon dioxide intact, it might explain the current composition without requiring exotic formation conditions. But the chemical anomalies didn't stop with carbon dioxide dominance. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent emission lines from nickel atoms with surprisingly weak corresponding signatures from iron. This represents a significant departure from typical solar system compositions, where iron and nickel occur in roughly solar proportions, reflecting the elemental abundances of the stellar nebula from which they condensed. The apparent depletion of iron relative to nickel in 3I Atlas raises fundamental questions about its formation environment or subsequent evolution. One speculative possibility involves differential processing of metallic components during the object's interstellar journey. Iron and nickel have different sublimation temperatures and chemical reactivity, so prolonged exposure to cosmic radiation or interstellar dust impacts might selectively remove iron while preserving nickel in more stable chemical forms. Another intriguing hypothesis involves the possibility that 3 Atlas formed in a stellar environment with non-solar elemental abundances. If its parent star belonged to a different galactic population, perhaps the thick disk or halo components that contain stars with unusual chemical compositions, the resulting planetary debris might naturally exhibit iron to nickel ratios unlike those seen in our local cosmic neighborhood. As summer turned to autumn and 3I Atlas approached its October perihelion, its tail structure became increasingly complex and visually spectacular. Ground-based observations from facilities like the Gemini Observatory documented multiple tail components with different orientations, colors, and apparent particle sizes. This multi-component structure suggested ongoing activation of different volatile reservoirs across various regions of the nucleus. The object was literally coming alive under solar heating after potentially billions of years in the cold emptiness between stars. The physics behind this complex tail development involves the selective sublimation of different ice species. As the comet encounters increasing solar heating, carbon dioxide begins outgassing at much greater distances from the sun than water ice, potentially creating an initial CO2-dominated coma and tail structure. As the object approaches closer to perihelion, water ice activation might trigger a second phase of tail development with different optical properties and dynamical behavior. Polarimetry measurements, which analyze the polarization state of scattered sunlight from the comet's coma and tail, provided additional clues about the nature of dust particles being ejected from the nucleus. The polarization signature suggested dust grains with unusual size distributions or optical properties compared to typical solar system comets. This could indicate either different formation processes in the original protoplanetary disk or extensive modification during the long interstellar journey. One particularly intriguing aspect of 3I Atlas's behavior involved apparent episodic brightenings that seemed to occur independently of its distance from the sun's position. Most comets follow predictable brightening curves as they approach perihelion, with brightness increasing smoothly as a function of decreasing solar distance. But 3I Atlas displayed periodic flare-ups that suggested more complex internal processes. These outbursts might result from the sudden exposure of fresh, volatile-rich material as surface crusts are stripped away by solar heating. Many comets develop insulating mantles of dust and processed organics that suppress sublimation until thermal stresses or gas pressure ruptures these protective layers. When breakthrough occurs, the underlying pristine ices can sublime rapidly, creating dramatic temporary increases in activity. Alternatively, the episodic behavior might reflect internal structural changes as 3I Atlas adapted to solar heating after potentially billions of years in the cold emptiness of interstellar space. Temperature gradients penetrating into the nucleus could trigger subsurface sublimation that fractures internal ice deposits, exposing new surfaces to solar radiation and creating cascading activation events. The rotational behavior of 3I Atlas also appeared anomalous compared to typical solar system comets. Photometric observations designed to measure brightness variations as the nucleus rotated revealed either an unusually long rotation period or a complex tumbling motion that made period determination difficult. This might indicate structural modifications during its interstellar journey or simply reflect the original angular momentum state from whatever event ejected it from its parent system. But perhaps the most unsettling aspect of 3 Atlas's behavior was how normal it appeared in some respects while being completely unprecedented in others. The basic physics of coma formation, tail development, and volatile sublimation followed well-understood principles. Yet the specific chemical signatures, temporal evolution, and structural properties seemed to violate every expectation based on decades of comet research. This combination of familiar and alien characteristics suggested that 3I Atlas represented something genuinely new in astronomical experience, not just another comet from another star system, but a window into planetary formation, processes, and stellar environments fundamentally different from our local cosmic neighborhood. The object was simultaneously confirming and challenging our understanding of how planetary systems evolve and what kinds of debris they can eject into the galaxy. As 3I Atlas approached its final weeks before perihelion passage and temporary disappearance behind solar glare, the accumulating observational evidence painted a picture of an object that defied easy categorization. It was clearly a comet based on its activity and spectroscopic properties. Yet its chemistry and behavior patterns matched no known class of solar system objects. The question was whether these anomalies reflected genuinely exotic physics and chemistry, or simply represented the extreme end of natural variation in planetary system debris, and that question would have to wait for resolution until December, when 3 Atlas would emerge from its solar hiding place and present telescopes with their best opportunity for detailed characterization. But even as astronomers prepared for months of intensive observations, a different kind of speculation was beginning to emerge from the data. Because while 3I Atlas's weird behaviors could potentially be explained through exotic but natural processes, they also raised uncomfortable questions about whether we were dealing with something more than just an unusually active comet from another star system. Part 8. Alien Tech or Natural Wonder. In the age of social media and viral conspiracy theories, it was perhaps inevitable that 3I Atlas would eventually face the question that has haunted every unusual astronomical discovery since the dawn of the space age. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemistry, complex behaviors, and remarkably convenient timing for observation had conspiracy theorists working overtime by late September 2025. The speculation began innocently enough in academic circles, where researchers noted similarities between 3I Atlas and the controversial Object 1 Oumuamua that had sparked debates about possible artificial origins in 2017. Both were interstellar visitors. Both displayed unusual properties that challenged conventional understanding. Both arrived with trajectories that provided excellent observing opportunities for human astronomers. But the similarities largely ended there, and the differences were profound and telling. Unlike Oumuamua's enigmatic cigar-like shape and mysterious non-gravitational acceleration without visible outgassing, 3I Atlas behaved exactly like what it appeared to be, a comet. It developed a classic coma and tail structure as it approached the sun's location. Its brightness variations followed predictable patterns based on volatile sublimation. Its trajectory showed the expected gravitational deflection from solar interaction with additional perturbations easily explained by outgassing forces. Most importantly, 3I Atlas exhibited no signs of controlled or directed motion. Its path through the solar system followed the precise hyperbolic trajectory expected for an unbound visitor under the influence of solar gravity alone. There were no course corrections, no unexplained accelerations, no radio transmissions, no geometric shapes or artificial structures visible even under the highest resolution observations available to human telescopes. The scientific method demands extraordinary evidence for extraordinary claims, and the evidence for 3I Atlas consistently pointed toward natural phenomena, albeit natural phenomena unlike anything previously observed in our cosmic neighborhood. Every strange behavior, every unusual chemical signature, every anomalous physical property had plausible explanations rooted in well-established physics and chemistry. Consider the extreme carbon dioxide dominance that made 3I Atlas's chemistry so remarkable. While unprecedented in solar system comets, this composition could easily result from formation in the outer regions of an unusual planetary system. Stars with different masses, metallicities, or planetary architectures might naturally produce comets with chemical signatures that seem alien to observers familiar only with our local solar system's products. The apparent iron depletion relative to nickel, while puzzling, could reflect either formation in a stellar environment with non-solar elemental ratios or subsequent processing during billions of years of interstellar travel. Cosmic ray bombardment, interstellar dust impacts, and thermal cycling in the cold depths of space might selectively alter surface compositions in ways that create unusual spectroscopic signatures without requiring any artificial intervention. Even the complex multi-component tail structure and episodic brightening events had precedence in solar system comets, though admittedly at the extreme end of observed behaviors. Comet Hale-Bopp displayed multiple tail components with different compositions. Comet Holmes underwent a dramatic outburst that increased its brightness by a factor of nearly 1 million in 2007. Natural processes were clearly capable of producing the kinds of spectacular and unusual behaviors observed in 3 Atlas. The real question wasn't whether 3I Atlas could be artificial. It was why people kept asking. Part of the answer lay in the profound psychological impact of contemplating truly interstellar scales. When we observe objects from other star systems, we're confronting the possibility that intelligence might exist elsewhere in the galaxy. The human mind evolved to navigate social hierarchies and detect agency. In complex environments, naturally looks for signs of purpose or intention in unexplained phenomena. This tendency becomes even stronger when dealing with objects that seem to violate our expectations or display properties that stretch the limits of conventional explanation. 3. I-Atlas's unusual chemistry and convenient observing geometry triggered the same pattern recognition systems that our ancestors used to identify potential predators or allies. When faced with something unprecedented, the brain's default assumption is often that someone or something must be responsible. But nature routinely produces phenomena that exceed human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under conditions ranging from the interiors of massive stars to the near absolute zero temperatures of interstellar space. The fact that we occasionally encounter natural processes or objects that surprise us is not evidence of artificial origin. It's evidence that our understanding of cosmic phenomena remains fundamentally incomplete. The media landscape surrounding astronomical discoveries also tends to amplify speculation about artificial origins. Headlines reading "Scientists baffled by mysterious interstellar visitor" generate more clicks than "Researchers study unusual but natural comet," regardless of which headline more accurately reflects the scientific consensus. This creates a feedback loop where public interest drives sensationalized coverage, which in turn feeds more speculation about exotic explanations. Social media compounds this effect by allowing unfiltered speculation to spread faster than careful scientific analysis. By the time astronomers have collected sufficient data to characterize an object's properties and rule out artificial origins, alternative theories have already achieved viral status and become resistant to correction through factual information. The historical pattern is clear and consistent. Every unusual astronomical discovery, from pulsars to fast radio bursts, has initially faced speculation about possible artificial origins. In every case, continued observation and analysis have revealed natural explanations that, while often more complex and fascinating than initially anticipated, require no involvement of extraterrestrial intelligence. This doesn't mean we should abandon the search for evidence of extraterrestrial technology. The universe almost certainly contains other intelligent civilizations, and some of them might be capable of interstellar travel or communication. But the detection of such civilizations will require clear, unambiguous evidence of artificial origin, coherent radio signals with information content, objects displaying controlled motion, inconsistent with natural forces or structures that violate the laws of physics as we understand them. 3. I-Atlas displayed none of these characteristics. Its radio emissions were detected consisted entirely of natural thermal radiation and molecular line emissions typical of cometary outgassing. Its trajectory followed predictable gravitational mechanics, with perturbations easily explained by volatile sublimation. Its internal structure, as revealed by thermal modeling and photometric observations, was consistent with a loose aggregate of ice and rock held together by weak gravitational and cohesive forces. Perhaps most tellingly, 3I Atlas was behaving exactly like what we would expect from the debris of planetary formation around other stars. Theoretical models to predict that every star system should eject significant quantities of small bodies during its formation and early evolution. These objects would wander through interstellar space for millions or billions of years before occasionally encountering other stellar systems where they might be observed as interstellar visitors. The chemistry and physical properties of such objects should reflect the conditions in their parent systems: different stellar masses, different elemental abundances, different planetary configurations, different thermal histories. An authentic sample of another star system's debris should look alien compared to solar system objects while still obeying the same fundamental laws of physics and chemistry that govern matter throughout the universe. In other words, 3I Atlas looked exactly like what it claimed to be, a natural product of planetary system formation around another star carrying chemical signatures that reflect formation conditions different from those that produced our local solar system family. The fact that it seemed strange to human observers was not evidence of artificial origin, but rather confirmation that we live in a galaxy where conditions for planetary formation vary dramatically from system to system. As 3I Atlas continued its approach toward perihelion, the accumulated evidence consistently supported natural explanations for its unusual properties. But that raised an even more intriguing question than whether it might be artificial. Where exactly had this ancient wanderer spent the billions of years between its ejection from whatever star system created it and its recent arrival in our cosmic neighborhood? The answer to that question would require sophisticated modeling of galactic dynamics and stellar motions across geological timescales. But preliminary attempts to trace 3I Atlas's trajectory backward through space and time were already yielding tantalizing clues about the object's origins and the remarkable journey that had brought it to our telescopes at precisely the right moment for detailed study. Part 9: Origins and Biography of 3I Atlas. Tracing the biography of an interstellar visitor requires reconstructing a journey that may have lasted longer than Earth has existed. 3I Atlas carries within its chemistry and trajectory the fossilized record of cosmic events that unfolded billions of years ago when our galaxy was younger and the distribution of stars and heavy elements was dramatically different from today's configuration. The first clues to the object's ancient origins emerge from kinematic analysis mathematical modeling that attempts to trace its motion backward through space and time. Preliminary calculations by researchers at the European Southern Observatory suggest that 3I Atlas may have originated from the galactic thick disk, a population of stars that formed during the Milky Way's early evolution between 7 and 12 billion years ago. If these kinematic models prove correct, 3I Atlas would be older than our entire solar system. It would have been wandering through interstellar space since before the Sun condensed from its parent molecular cloud, carrying chemical signatures from an era when star formation rates were higher, and the galaxy's heavy element content was substantially different from today's values. The thick disk hypothesis gained support from the object's unusual chemistry. Stars in this ancient galactic component typically show different elemental abundance patterns compared to younger thin disk populations like our Sun's. The apparent iron depletion and extreme carbon dioxide content observed in 3I Atlas might reflect formation around a thick disk star with non-solar metallicity and unusual volatile chemistry. But how does a small body escape from its parent stellar system and begin the long journey through interstellar space? The ejection process typically involves gravitational interactions with giant planets during the chaotic early phases of planetary system evolution. As massive worlds migrate inward or outward due to interactions with protoplanetary disk material, they can scatter smaller objects onto hyperbolic trajectories that carry them out of the system entirely. Computer simulations suggest that every planetary system ejects vast quantities of debris during its formation. For every kilogram of material that remains gravitationally bound in planets, asteroids, and comets, perhaps 10 kilograms gets flung into interstellar space by gravitational slingshot effects. This means The galaxy should be populated with trillions of wandering fragments from billions of stellar nurseries, a vast diaspora of planetary construction debris drifting between the stars. Once ejected from its parent system, 3I Atlas would have begun a solitary odyssey through the near vacuum of interstellar space. The typical density of matter between stars is roughly 1 atom per cubic centimeter, a better vacuum than anything achievable in terrestrial laboratories. In this environment, the object would have been essentially isolated from external influences, preserved in cosmic deep freeze at temperatures just a few degrees above absolute zero. Yet this interstellar journey was not entirely uneventful. Recent modeling by galactic dynamics specialists has identified several close encounters with other stellar systems during 3I Atlas's long voyage. Over the past 10 million years alone, the object appears to have passed within 1 parsec, approximately 3 light years, of at least half a dozen different stars, each encounter potentially altering its trajectory through subtle gravitational perturbations. The most significant of these stellar encounters occurred approximately 4 million years ago, when 3I Atlas passed within roughly 1 light year of a red dwarf star in the constellation Cassiopeia. The gravitational influence of this close approach would have been sufficient to measurably deflect the object's trajectory, potentially explaining why its current motion doesn't point back toward any obvious parent system in the galaxy's thick disk population. This raises fascinating questions about the object's surface evolution during its interstellar voyage. Cosmic ray bombardment over millions of years would have gradually altered the chemistry of exposed ice and rock surfaces through radiolysis and nuclear spallation reactions. High-energy particles from distant supernovae and other galactic phenomena would have broken chemical bonds, created exotic isotopic ratios, and possibly generated entirely new molecular species not found in typical solar system materials. The extremely cold temperatures of interstellar space, typically around 3 Kelvin, would have preserved most volatile materials in solid form throughout the journey. But periodic encounters with interstellar dust clouds or the radiation fields of nearby stars might have caused episodic heating events that could sublimate surface layers and redeposit them in different configurations. This could explain some of the unusual chemistry observed by modern telescopes. Perhaps most remarkably, 3I Atlas has maintained structural integrity throughout its billion-year journey despite being subjected to thermal, cycling cosmic ray bombardment and occasional impacts with interstellar dust grains. This suggests either unusually robust construction or continual self-repair through sublimation and redeposition processes that gradually heal micrometeorite damage and radiation-induced structural changes. The object's arrival in our solar system represents the culmination of a journey that defies human comprehension. Consider the navigational precision required for 3I Atlas to arrive at precisely the right time and trajectory for optimal observation by 21st century human telescopes. The object had to survive billions of years in the hostile environment of interstellar space, navigate gravitational influences from dozens of stellar encounters, and arrive during the brief historical moment when humanity possessed the technological capability to recognize and study it. This timing seems almost too perfect to be coincidental. 3I Atlas approached perihelion just as our most advanced space telescopes were coming online and our understanding of interstellar chemistry was sophisticated enough to appreciate its significance. A few centuries earlier, it would have been dismissed as just another fuzzy star. A few centuries later, it might have been detected but not properly characterized before disappearing back into the cosmic deep. The biography of 3I Atlas also illuminates the broader story of galactic evolution and the cosmic recycling of planetary materials. Every heavy element in the object's composition was forged in the nuclear furnaces of ancient stars and distributed through space by supernovae explosions. The carbon, oxygen, silicon, and trace metals that make up its structure represent the accumulated stellar alchemy of countless generations of stars that lived and died before our solar system even existed. In a very real sense, 3 Atlas serves as a messenger from the ancient galaxy carrying samples of planetary formation processes that occurred under conditions dramatically different from those that created Earth and its celestial companions. The object's chemistry provides direct evidence of how volatile materials condense and evolve in stellar environments with different masses, metallicities, and dynamical histories. But perhaps the most profound aspect of 3 Atlas's biography is what it reveals about the interconnectedness of galactic-scale processes. This object began its existence as part of a planet-forming disk around another star, possibly in a completely different region of the galaxy. Through a complex chain of gravitational interactions, stellar motions, and cosmic accidents, it eventually found its way to our telescopes, carrying information about its origins across vast distances and timescales. The thick disk origin hypothesis, if confirmed, would make 3I Atlas a fossil from the Milky Way's youth, a time when the galaxy was more actively forming stars, and the chemical composition of interstellar space was substantially different from today's values. Studying this ancient wanderer could provide insights into galactic chemical evolution, early planetary formation processes, and the distribution of volatile materials in the primordial galaxy. Yet for all the sophisticated modeling and chemical analysis, fundamental questions about 3I Atlas's origins remain unanswered. We cannot definitively identify its parent star or the planetary system where it formed. The gravitational chaos of galactic evolution has erased most traces of its original trajectory, leaving only statistical hints about its possible thick disk provenance. This uncertainty reflects the inherent challenges of interstellar archaeology. Unlike terrestrial fossils, which remain embedded in datable rock layers, cosmic travelers like 3 Atlas carry no direct evidence of when or where they originated. Their stories must be reconstructed through indirect clues, chemical composition, isotopic ratios, trajectory analysis, and statistical modeling of galactic dynamics. But these limitations don't diminish the significance of what 3 Atlas represents. Even without knowing its exact birthplace, we can be confident that it carries authentic samples from another world formed under conditions different from those in our solar system. Every spectroscopic observation and chemical analysis provides new data about the diversity of planetary formation processes and the range of environments where worlds can emerge around other stars. As 3I Atlas continued its final approach toward perihelion in late October 2025, astronomers were preparing for the object's temporary disappearance behind solar glare. The weeks immediately surrounding perihelion would be the most scientifically valuable period of the entire encounter, when maximum solar heating would drive the highest levels of outgassing and potentially reveal subsurface materials that had been preserved since the object's formation billions of years ago. But the solar glare that would hide 3I Atlas during its most active phase also added an element of suspense to the unfolding story. Would the object survive perihelion intact, or would thermal stresses fragment it into multiple pieces like so many comets before it? When it re-emerged into telescopic view in December, would it still display the same unusual chemistry and complex activity patterns that had made it so remarkable during its inbound approach? The answers to these questions would have to wait. But in the meantime, the September surge and 3I Atlas's remarkable properties were raising uncomfortable possibilities about the nature of our cosmic neighborhood and humanity's place within it. Were we witnessing a random convergence of unrelated phenomena? Or could there be deeper patterns at work that connected the interstellar visitor to the unusual clustering of near-Earth object encounters? Some researchers were beginning to wonder whether the September events represented not just statistical coincidence, but the opening act of something much larger, a cosmic drama playing out on scales that might dwarf human understanding of celestial mechanics and galactic evolution. Part 10. Spectacular what-ifs. Cosmic dominoes. The human imagination, when confronted with phenomena that exceed our everyday experience, tends towards spectacular explanations. In the case of 3I Atlas and the September surge, speculation began emerging about possible cascade effects. The idea that an interstellar visitor might somehow trigger a chain reaction of cosmic events that could fundamentally alter our solar system's dynamics. Could 3I Atlas be gravitationally stirring up the asteroid population like a cosmic spoon mixing ingredients in a celestial soup? The mathematics argue decisively against this romantic notion. Even at its maximum estimated mass of several trillion kilograms, 3I Atlas represents a gravitational minnow in the vast ocean of solar system dynamics. Its influence on near-Earth objects at distances of millions of kilometers would be utterly negligible compared to the overwhelming gravitational dominance of the Sun and planets. Newton's inverse square law is unforgiving in its mathematical precision. Gravitational effects diminish with the square of distance, meaning that 3I Atlas's ability to influence other objects drops to essentially zero at the scales involved in the September encounters. To put this in perspective, the gravitational tug between 3I Atlas and asteroid FA22 during their simultaneous presence in the inner solar system would be roughly equivalent to the gravitational attraction between two automobiles parked in neighboring cities. Yet the persistence of gravitational shepherding theories reveals something important about human psychology and our relationship with cosmic phenomena. We instinctively search for causal connections between simultaneous events, even when the underlying physics makes such connections impossible. This tendency served our ancestors well when identifying cause and effect relationships in terrestrial environments, but it can lead us astray when applied to astronomical phenomena operating on scales that dwarf human experience. More exotic cascade scenarios involve possible connections between 3I Atlas and solar activity. Could an interstellar visitor somehow trigger increased solar flaring or coronal mass ejections that might affect space weather around Earth? This idea taps into legitimate concerns about solar-terrestrial interactions and the vulnerability of modern technological civilization to geomagnetic storms. However, the physics of solar dynamics operate on energy scales that make comet-solar interactions essentially irrelevant. The Sun releases approximately 3.8 times 10 to the 26th watts of energy, continuously more power in 1 second than human civilization has consumed throughout all of recorded history. The gravitational and electromagnetic influence of a small interstellar comet at distances exceeding 100 million kilometers would be completely overwhelmed by the much larger forces that drive solar variability. Solar activity follows well-documented cycles related to the Sun's internal magnetic dynamo, not the presence or absence of small visitors in the outer reaches of the solar system. Correlation between comet appearances and solar events occasionally occurs by pure chance, but these coincidences represent statistical noise rather than causal relationships. The meteor shower scenario presents another tempting but ultimately unsupported speculation. Could 3I Atlas be trailing a debris stream that might produce spectacular meteor displays when Earth passes through the material? This idea gains superficial plausibility from the fact that many annual meteor showers result from Earth encountering debris streams left behind by comets. But interstellar meteor streams face fundamental physics problems that make them essentially undetectable from Earth. The debris ejected from 3I Atlas carries the same hyperbolic velocity as the parent object, meaning any particles it sheds will also escape the solar system rather than settling into stable orbits that could intersect Earth's path. By the time our planet reaches the region where 3 Atlas passed through, any ejected material will have dispersed across volumes of space so vast that the particle density becomes negligible. Moreover, the high relative velocities involved in interstellar encounters mean that any debris particles that did somehow encounter Earth would impact our atmosphere at speeds exceeding 70 kilometers per second, much faster than typical solar system meteors. Such high-velocity impacts would produce brief, bright flashes rather than the prolonged trails that characterize normal meteor showers. The fragmentation fantasy represents yet another attempt to find hidden connections between 3I Atlas and the September asteroid encounters. Could FA-22 and the other near-Earth objects be fragments of the interstellar visitor broken off during some previous passage through the inner solar system and now following independent orbits that bring them back to Earth's vicinity? This scenario faces insurmountable problems with orbital mechanics and chemical composition. True fragments from 3I Atlas would retain hyperbolic trajectories and interstellar chemistry similar to the parent object. The September asteroids display neither characteristic. Their elliptical orbits and typical carbonaceous or silicate compositions indicate conventional solar system origins with no connection to interstellar material. Perhaps the most mundane explanation is also the most likely. We're witnessing the statistical equivalent of multiple lightning strikes, improbable individual events that occasionally cluster together through pure chance. The universe contains no obligation to distribute cosmic encounters evenly across human timescales. Random processes can and do produce apparent patterns that seem meaningful to pattern-seeking intelligence. The rapid expansion of survey capabilities in the mid-2020s means we're observing this cosmic neighborhood with unprecedented sensitivity and cadence. Previous generations of astronomers might have missed most of the September encounters entirely or detected them as isolated events spread across different news cycles. Our current ability to discover, track, and characterize multiple near-Earth objects simultaneously creates opportunities for apparent clustering that didn't exist during earlier epochs of astronomical observation. Yet even as rational analysis argues for coincidence and observational bias, the nagging sense of orchestrated timing persists. 3I Atlas's precise arrival during a period of enhanced near-Earth object activity combined with its unprecedented chemical signatures and ancient origins, suggests that we may be witnessing something more significant than a random convergence of unrelated events. The answer may not emerge until we've had months to study 3I Atlas in detail following its December re-emergence from solar glare. Detailed spectroscopic analysis, precise trajectory measurements, and careful comparison with the September asteroid population might reveal connections that aren't apparent in preliminary observations. But if no such connections emerge, if 3I Atlas proves to be genuinely isolated from the September encounters, then we're left with an even more intriguing possibility. Perhaps the universe is simply more active and interconnected than our Earth-centric perspective typically allows us to appreciate. Maybe what seems like an extraordinary convergence from our limited viewpoint is actually business as usual on galactic scales. The question isn't whether something is following 3I Atlas. The question is whether we're finally developing the observational capability to perceive the true complexity of the cosmic environment we've always inhabited. And if that's the case, then the September surge may be just the beginning of our education about what it means to be citizens of a galaxy where 400 billion stars are constantly exchanging material across the vast expanses of interstellar space. But before we can answer those larger questions, we need to understand why 3I Atlas itself is behaving so strangely. Because as autumn progressed and the interstellar visitor approached its closest encounter with the Sun, the telescopes around the world were documenting activity and chemical signatures unlike anything seen in previous comets, solar system or otherwise. Part 11, Observational Windows Late 2025 to 2026. The cosmic choreography of late 2025 was reaching its climax as 3I Atlas approached its date with solar destiny. October 30th marked the calculated perihelion passage, the moment when this ancient wanderer would sweep closest to our sun after a journey that may have lasted longer than Earth has existed. But this crucial encounter would unfold hidden from human eyes, masked by the overwhelming glare of our nearest star. For astronomers worldwide, the perihelion period represented both the most scientifically valuable phase of the entire encounter and the most frustrating observational challenge. This was when maximum solar heating would drive the highest levels of volatile sublimation, potentially exposing subsurface materials that had been preserved since the object's formation billions of years ago. Chemical species that remained locked in solid form during the long interstellar journey would finally transition to vapor phase, revealing their spectroscopic signatures to any telescope capable of detecting them. But the same solar radiation that promised to unlock 3I Atlas's deepest secrets would also render it effectively invisible from Earth. The object's trajectory carried it to within approximately 0.4 astronomical units of the Sun, roughly 60 million kilometers closer than Mercury's orbital distance. From Earth's perspective, this placed 3I Atlas less than 10 degrees from the solar disk, buried in the twilight glow that makes precision astronomy impossible. The enforced observational hiatus created a tantalizing mystery. Would 3I Atlas survive perihelion intact, emerging in December as a single coherent object with enhanced activity driven by fresh volatile exposure? Or would thermal stresses fracture its internal structure, breaking it apart into multiple fragments that would create an expanding debris cloud visible as separate cometary objects? The survival question carried implications far beyond academic curiosity. Intact survival would suggest that interstellar objects possess sufficient structural integrity to preserve ancient chemical signatures even when subjected to intense solar heating. Fragmentation, while spectacularly photogenic, might disperse the very materials that made 3I Atlas scientifically valuable, transforming a pristine sample from another star system into a collection of processed debris streams. Historical precedent offered little guidance. Most solar system comets that fragment during close solar approaches are fresh visitors from the Oort cloud, making their first encounter with significant solar radiation after millions of years in cold storage. 3I Atlas, by contrast, was a battle-tested survivor that had already demonstrated remarkable structural stability during its billion-year journey through interstellar space. The cosmic irony was palpable. After traveling unimaginable distances across space and time to reach our solar system, 3I Atlas would spend its most active and revealing moments hidden behind the very star that was driving its spectacular transformation. It was like attending a concert where the featured performer disappeared behind a curtain during their most important song. But astronomical patience has its rewards. Earth's orbital motion around the Sun gradually improves viewing geometry for objects that pass close to our star, and by early December 3I Atlas would begin emerging from the solar glare into prime observing position. The object's closest approach to Earth was calculated for mid-December at a distance of approximately 1.8 astronomical units, roughly 270 million kilometers. This distance might seem vast by terrestrial standards, but it represented optimal conditions for detailed spectroscopic analysis, close enough for major telescopes to collect substantial amounts of light, far enough to avoid atmospheric interference from Earth's own thermal radiation, and positioned in the pre-dawn sky, where the background contamination would be minimal. The December observing window would likely represent the best opportunity to study intact interstellar material that human science might encounter for decades or centuries. Unlike 1I Oumuamua's brief visit and rapid departure, 3I Atlas's trajectory and timing would keep it within range of major observatories well into 2026, providing months of sustained observation across multiple wavelength ranges. Meanwhile, other members of the September cosmic cast were preparing for their own observational moments. Comet C 2025 R2 Swan's discovery that had been brightening throughout autumn faced its own survival challenge as it approached perihelion in early November. Fresh comets from the outer solar system often fragment under solar heating, but if Swan survived, it promised to provide spectacular naked-eye viewing for observers in the northern hemisphere. The comet's visibility window was narrowing as its trajectory carried it deeper into the evening twilight, but experienced comet hunters were reporting possible naked-eye detection under dark rural skies. Binoculars revealed a distinctive greenish coma and growing tail structure pointing away from the sun, classic signatures of active volatile sublimation. Whether this display would continue or end in catastrophic fragmentation remained to be seen. Asteroid 99942, Apophis, continued its inexorable approach toward the April 2029 encounter that would bring it closer to Earth than our geostationary satellites. While still 3.5 years away, ground-based telescopes were already beginning extended characterization campaigns designed to map the asteroid's surface, properties, rotation state and internal structure before the close flyby altered these characteristics. NASA's OSIRIS-APEX spacecraft en route to rendezvous with Apophis after its Earth encounter was conducting periodic check-ins and navigation adjustments during its multi-year cruise phase. The spacecraft would arrive at Apophis in June 2029, providing close-up observations of how the gravitational interaction with Earth had modified the asteroid's physical properties. But the most dramatic enhancement to our cosmic surveillance capabilities was still ramping up operations. The Vera C. Rubin Observatory's first light images had demonstrated unprecedented ability to discover and track near-Earth objects, but the facility was still in commissioning phase during autumn 2025. Once fully operational, Rubin would rescan the entire accessible sky every few nights, providing near real-time monitoring of cosmic traffic in our local neighborhood. This enhanced cadence would revolutionize asteroid detection and tracking, potentially revealing that the September surge was not an anomalous clustering, but rather a representative sample of the true activity level in near-Earth space. Previous surveys operating with much longer intervals between observations might have missed many objects or failed to recognize clustering patterns that would be obvious under continuous surveillance. The space-based component of our detection network was also preparing for major upgrades. NASA's Near-Earth Object Surveyor, scheduled for launch in September 2027, would deploy an infrared telescope specifically optimized for asteroid detection. Operating from a position trailing Earth in our solar orbit, NEO Surveyor would be able to detect objects approaching from the sunward direction that remain invisible to ground-based surveys. This capability would finally close the detection gap that allowed the Chelyabinsk impactor to arrive completely unnoticed in 2013. Once operational, NEO Surveyor should provide advanced warning of incoming objects regardless of their approach direction, eliminating the solar blind spot that represents our most significant planetary defense vulnerability. For amateur astronomers and citizen scientists, the late 2025 period offered multiple opportunities for meaningful contributions to ongoing research. Comet Swan remained within reach of modest telescopes and even sophisticated cameras, allowing dedicated observers to document changes in tail structure, brightness variations, and possible fragmentation events. 3. I-Atlas's December re-emergence would initially favor observers in the southern hemisphere, but its rapid motion across the sky would eventually bring it within range of northern observers as well. While the comet would be too faint for visual observation without substantial telescopic assistance, experienced astrophotographers could potentially capture images showing coma structure and tail development. More importantly, the coordinated observation of these multiple objects was providing valuable experience in international scientific cooperation and data sharing. The techniques and protocols developed for tracking 3I Atlas and characterizing the September surge would be directly applicable to future planetary defense scenarios involving potentially hazardous asteroids with short warning times. The observational challenges of late 2025 were also highlighting the importance of redundancy and international coordination in astronomical surveys. No single telescope or survey system could provide complete coverage of all possible approach directions and object types. Only through coordination between ground-based and space-based facilities across multiple wavelength ranges and observing cadences could we achieve comprehensive awareness of our cosmic neighborhood. As autumn progressed toward winter and 3 Atlas prepared for its hidden solar encounter, the global astronomical community was mobilizing resources for what might prove to be the most intensive characterization of interstellar material ever attempted. The stakes extended far beyond academic curiosity. The data collected during the December observing window could provide crucial insights into planetary formation, processes, galactic chemical evolution, and the frequency of interstellar material exchange between stellar systems. But first, 3I Atlas had to survive its appointment with our star. The answer to that question would remain hidden until December, when telescopes around the world would turn toward the pre-dawn sky to discover whether ancient chemistry from another star system had endured one final test in its billion-year journey to human science. Part 12. Imagining future scenarios and speculative pathways. The convergence of enhanced detection capabilities, improved deflection technologies, and growing international cooperation in the late 2020s sets the stage for multiple possible futures in humanity's relationship with cosmic threats. The September surge and 3I Atlas encounter provide glimpses of what these futures might look like, ranging from triumphant mastery of our cosmic environment to sobering reminders of our continued vulnerability. In the most optimistic scenario, the technological and institutional foundations laid during the 2020s mature into a robust planetary defense ecosystem that effectively eliminates asteroid impact risks while revolutionizing our understanding of the broader galactic environment. The Vera C. Rubin Observatory's unprecedented survey capabilities, combined with space-based infrared detection from NEO Surveyor and similar systems, create comprehensive awareness of incoming objects with decades or centuries of advanced warning. This extended lead time transforms deflection from desperate last-minute interventions into routine celestial traffic management. Gentle nudges applied years in advance divert potentially hazardous objects into safe trajectories using proven kinetic impact techniques refined through multiple DART-class missions. The process becomes so reliable and predictable that asteroid deflection joins earthquake prediction and hurricane tracking as accepted tools of natural disaster mitigation. Under this scenario, Comet Swan survives its 2025 perihelion passage and provides spectacular naked-eye viewing throughout the Northern Hemisphere winter, inspiring a new generation of amateur astronomers and science enthusiasts. 3I Atlas emerges intact from its solar encounter and yields unprecedented insights into interstellar chemistry and galactic material exchange processes. The detailed characterization of 3I Atlas establishes interstellar archaeology as a major scientific discipline. Improved survey systems detect dozens of additional interstellar visitors throughout the late 2020s, each one carrying unique chemical signatures that illuminate different aspects of planetary formation around other stars. By the early 2030s, systematic comparison of interstellar debris provides the first comprehensive survey of planetary chemistry across different galactic environments. This scientific windfall drives technological development in spectroscopy precision, astrometry, and coordinated multi-telescope observations. The same capabilities prove invaluable for characterizing potentially hazardous asteroids enabling precise determination of composition, structure, and deflection requirements well in advance of any actual threats. International cooperation flourishes under the pressure of shared cosmic challenges. The protocols developed for coordinating observations of 3I Atlas evolve into standardized procedures for handling any anomalous or threatening objects. Regular exercises and training programs maintain readiness while building confidence in global response capabilities. Public engagement with astronomy and space science reaches unprecedented levels as people worldwide follow the ongoing discoveries and characterization efforts. The combination of genuine cosmic threats and effective technological responses provides compelling evidence for the value of scientific research and international cooperation. But alternative scenarios present more challenging possibilities. The moderate pathway acknowledges that improved detection and deflection capabilities will inevitably encounter real tests as the catalog of potentially hazardous objects expands. Current surveys have identified most kilometer-plus asteroids capable of causing global catastrophe, but the inventory of city-killer-sized objects in the 100 to 300 meter range remains incomplete. Statistical projections suggest that one or more objects in this size range will eventually approach Earth with insufficient warning time for gentle deflection measures. These scenarios would require more aggressive intervention techniques, potentially including nuclear explosive devices that carry significant technical and political risks. The first such encounter might involve an object discovered only months or weeks before potential impact, forcing rapid decisions about deflection strategies under enormous time pressure and public scrutiny. Success would validate planetary defense investments and probably trigger expanded funding for detection and deflection capabilities. Failure could result in regional devastation and fundamental questions about humanity's ability to protect itself from cosmic threats. Even partial success scenarios carry significant implications. A deflection attempt that successfully prevents global catastrophe but fails to eliminate all impact risk might scatter debris across populated areas, creating multiple smaller impact sites instead of a single large crater. Public perception of such outcomes could shift from viewing planetary defense as heroic protection toward viewing it as dangerous meddling with natural processes. Ocean impacts present particularly complex challenges for both deflection strategy and public communication. The majority of Earth's surface is covered by water, making ocean impacts statistically more likely than land impacts for randomly arriving asteroids. But tsunami generation from ocean impacts remains poorly understood, with significant uncertainties in current modeling efforts. A 200-meter asteroid striking deep ocean could potentially generate 10-meter waves that remain dangerous across entire ocean basins. Coastal cities from Boston to Barcelona could face devastating tsunami impacts hours after a mid-Atlantic collision. The warning time provided by successful detection might be sufficient for evacuation efforts, but the economic and social disruption would be enormous even without direct casualties. These scenarios highlight the importance of accurate risk communication and realistic public expectations about planetary defense capabilities. Our current technology can probably handle most threats given sufficient advance warning, but late discovery scenarios or unusually large objects could overwhelm existing deflection capabilities. The worst-case scenarios, while statistically unlikely over human timescales, represent existential challenges that current technology cannot address effectively. A long-period comet from the Oort cloud could arrive with only months or years of advanced warning, carrying enough kinetic energy to threaten human civilization, regardless of deflection attempts. Such objects with diameters potentially exceeding 10 kilometers would require deflection energies far beyond anything available through kinetic impact techniques. Nuclear explosive deflection might be theoretically possible, but the required technology development, international coordination, and deployment timelines could easily exceed available warning periods. These extreme scenarios serve as reminders that planetary defense provides protection against most threats, not all threats. Like earthquake-resistant building codes or hurricane tracking systems, defensive measures can dramatically reduce risks without eliminating them entirely. The goal is not perfect security and impossible standard, but rather reasonable protection against reasonably likely threats. Population psychology and social dynamics introduce additional complications across all scenarios. Public reaction to asteroid threats depends heavily on risk communication strategies, media coverage patterns, and existing levels of trust in scientific and governmental institutions. Accurate information provided by credible sources can maintain social stability during crisis situations. Sensationalized reporting or conspiracy theories can undermine response effectiveness even when technical capabilities are adequate. The September surge provided valuable experience in managing public communication about cosmic threats, but real impact scenarios would involve much higher stakes and more intense media scrutiny. Social media amplification of both accurate information and misinformation could significantly complicate crisis management efforts. Economic implications also vary dramatically across different scenarios. Successful deflection of a major threat could generate enormous public support for continued investment in planetary defense capabilities. Failed or partially successful interventions might trigger more cautious approaches that emphasize evacuation and damage mitigation over active deflection attempts. The commercial space industry's growing involvement in asteroid-related activities introduces market dynamics that could either support or complicate planetary defense efforts. Private companies motivated by asteroid mining profits might develop characterization and rendezvous capabilities that serve dual purposes for both resource extraction and deflection missions. But commercial priorities don't always align with planetary defense needs. A potentially hazardous asteroid that also contains valuable resources might face competing claims from mining companies and deflection missions. These conflicts would require careful regulatory frameworks to balance commercial interests with public safety requirements. International politics represent perhaps the most unpredictable variable in future planetary defense scenarios. Current cooperation mechanisms work well during routine operations, but crisis situations involving potential impacts might trigger more competitive national responses. Countries might pursue independent deflection efforts rather than coordinating through international frameworks, potentially creating conflicting or counterproductive interventions. Technology development trajectories will also influence which scenarios become most likely. Breakthrough advances in fusion, propulsion, artificial intelligence, or materials science could dramatically expand deflection capabilities and extend effective warning times. Conversely, technological stagnation or reduced funding for space-based detection systems could leave us vulnerable to threats that current projections assume will be prepared to handle. Climate change and other global challenges compete for the same financial and political resources needed for planetary defense investments. Public and governmental attention has limited bandwidth, and asteroid threats that seem abstract or distant might lose priority relative to more immediate concerns like economic inequality, environmental degradation, or international conflicts. Yet the cosmic perspective provided by objects like 3 Atlas offers unique opportunities to transcend terrestrial divisions and focus on shared human interests. The knowledge that our planet exists within an active galactic environment filled with potential threats and opportunities could catalyze cooperation in ways that purely terrestrial challenges cannot achieve. As we stand at the threshold of potentially revolutionary improvements in our ability to monitor and manage cosmic threats, the futures that emerge will depend as much on our social and political choices as on our technological capabilities. The September surge and 3 Atlas encounter provide both inspiration and warning. about what lies ahead in humanity's relationship with the broader cosmic environment. But before any of these long-term scenarios can unfold, we must first learn what 3I Atlas reveals when it re-emerges from its solar hiding place in December. The chemical signatures and physical properties documented during that crucial observation window may provide our first detailed glimpse of authentic material from another star system and our first real understanding of what it means to be citizens of a galaxy where worlds constantly exchange their most precious substances across the vast distances between stars. Part 13. Conclusion. A cosmic perspective. As winter settles across the northern hemisphere and 3I Atlas prepares for its December reemergence from solar glare, we find ourselves at a remarkable inflection point in humanity's relationship with the cosmos. The events of September 2025, from FA22's close approach to Swan's brightening display to the discovery of our third confirmed interstellar visitor, have provided us with something far more valuable than scientific data or planetary defense validation. They have given us a new lens through which to view our place in the universe. For most of human history, the night sky appeared static and predictable. Stars wheeled overhead in eternal patterns, planets wandered along predetermined paths, and the occasional comet or shooting star provided brief reminders that space was not entirely empty. This perspective fostered a sense of cosmic isolation. Earth and its inhabitants seemed like unique products of local stellar processes fundamentally separated from the rest of the galaxy by unimaginable distances and timescales. The September surge shattered that illusion of isolation. We discovered that our solar system is not a quiet suburban neighborhood on the outskirts of cosmic activity, but rather a busy intersection where ancient travelers from distant worlds regularly pass through, carrying messages from their origins. 3I Atlas alone represents a direct physical connection to stellar processes that occurred billions of years ago in regions of the galaxy we may never visit with spacecraft. This represents more than just a scientific revelation. It constitutes a fundamental shift in cosmic perspective, comparable to the Copernican revolution or the discovery of the expanding universe. We are not isolated products of a single stellar system, but participants in galactic-scale processes that have been exchanging materials and information between worlds for longer than Earth has existed. The chemical signatures preserved in 3I Atlas's ancient ices carry information about stellar nucleosynthesis rates, planetary formation conditions, and volatile chemistry in environments that existed before our sun began to shine. Every spectroscopic observation provides direct sampling of processes that shaped the galaxy during its youth, when star formation rates were higher and the distribution of heavy elements was dramatically different from today's configuration. But perhaps most importantly, the September events have demonstrated that we now possess the technological capability to recognize, study, and potentially interact with this galactic-scale system of material exchange. The same detection networks that tracked FA22's approach and will monitor Apophis's 2029 flyby can also identify and characterize interstellar visitors like 3I Atlas with sufficient precision to extract detailed scientific information. We have graduated from passive observers of cosmic phenomena to active participants in interstellar archaeology. Every new survey telescope that comes online, every improved spectroscopic technique that gets developed, every international cooperation agreement that gets signed brings us closer to comprehensive understanding of our galactic neighborhood and our role within it. This transition carries profound implications that extend far beyond astronomy and planetary defense. The infrastructure required for monitoring cosmic threats and studying interstellar visitors, precision detection systems, rapid response capabilities, international coordination mechanisms, provides templates for addressing other global challenges that transcend national boundaries. Climate change, pandemic response, resource management, and environmental protection All require similar combinations of scientific understanding, technological capability, and international cooperation. The lessons learned from tracking asteroids and characterizing comets could prove equally valuable for monitoring greenhouse gas concentrations, predicting disease outbreaks, or managing shared ocean and atmospheric resources. More fundamentally, the cosmic perspective fostered by awareness of interstellar visitors like Three-Eye Atlas offers an antidote to the parochial thinking that often hampers cooperation on global issues. When we recognize that Earth exists within a dynamic galactic ecosystem, where material constantly flows between stellar systems across vast distances and timescales, terrestrial divisions based on nationality, ideology, or economic system begin to seem less significant. We are all passengers on the same small planet, threading its way through a galaxy filled with ancient debris from billions of other worlds. The carbon atoms in our bodies were forged in stellar furnaces that died before the sun was born. The water we drink may have arrived via comets from the outer reaches of our solar system. The air we breathe contains elements that have traveled between stars for longer than complex life has existed on Earth. This understanding transforms environmental protection and social cooperation from abstract moral imperatives into practical necessities for cosmic citizenship. We cannot afford to waste the rare and precious conditions that allow complex chemistry and biological evolution to flourish on planetary surfaces, nor can we afford to fragment our response capabilities through short-sighted competition when dealing with challenges that operate on galactic scales. The September surge has also highlighted how much we still don't know about our cosmic neighborhood and the processes that govern it. Current models predict that interstellar visitors should be relatively rare, perhaps one detectable object every few years under optimal observing conditions. But if Three-Eye Atlas represents typical rather than exceptional activity levels, our estimates might be off by orders of magnitude. The Vera C. Rubin Observatory and other next-generation survey systems could reveal that dozens or hundreds of interstellar objects pass through our solar system annually, most of them too small or dark to detect with current technology. This would transform our understanding of galactic material exchange rates and the frequency of information transfer between stellar systems. Such discoveries would also raise profound questions about the prevalence of complex chemistry and potentially biological processes throughout the galaxy. If interstellar space is filled with organic compounds and volatile materials that originated in diverse planetary environments, then the ingredients for life might be distributed far more widely than we currently realize. Every comet that enters our solar system, whether from the local Oort cloud or distant interstellar space, carries samples of the chemical conditions that existed during its formation. These natural laboratories provide direct access to processes and environments that remain beyond the reach of our most ambitious spacecraft missions. But studying these cosmic messengers requires continued investment in the detection, tracking, and characterization capabilities that made the September discoveries possible. The technologies and institutional frameworks that allowed us to identify Three-Eye Atlas as an interstellar visitor and track FA-22's safe passage represent decades of scientific development and international cooperation. These capabilities are not self-maintaining. They require ongoing funding, technological upgrades, and political support from governments and institutions worldwide. The long intervals between major impact threats or spectacular interstellar visitors can make it tempting to reduce investments in planetary defense and cosmic surveillance systems. This would be a profound mistake. The September surge has shown us that our cosmic neighborhood is far more active and interconnected than we previously realized. We are finally developing the observational and analytical tools needed to understand our place within galactic-scale processes that have been operating for billions of years. The coming decades could witness revolutionary advances in our understanding of planetary formation, stellar evolution, and galactic chemical evolution based on direct sampling of interstellar materials delivered to our telescopes by natural cosmic processes, but only if we maintain and expand the capabilities that made these discoveries possible. The choice before us is clear. We can embrace our role as cosmic citizens, investing in the technologies and institutions needed to monitor and understand our galactic environment while protecting our planet from cosmic threats, or we can retreat into terrestrial parochialism, abandoning the cosmic perspective, just as we're beginning to glimpse the true complexity and wonder of the universe we inhabit. The September surge and 3I Atlas encounter argue powerfully for the first path. We have been given unprecedented opportunities to study authentic samples from other star systems while demonstrating our growing capability to protect Earth from cosmic threats. These achievements represent the beginning of humanity's transition from a planet-bound species to active participants in galactic-scale phenomena. But this transition will only succeed if we maintain the curiosity, cooperation, and commitment to scientific understanding that made it possible. The cosmos has delivered remarkable gifts to our telescopes and detection networks. Whether we prove worthy of these gifts will depend on the choices we make in the months and years ahead. As 3I Atlas prepares to re-emerge from behind the solar glare carrying chemical signatures from another star system and another era of galactic evolution, we stand ready to receive its messages about planetary formation, processes, and cosmic material exchange that we could never study any other way. What we learn from this ancient wanderer may reshape our understanding of how worlds form around other stars, how life-essential materials get distributed throughout the galaxy, and what it truly means to be cosmic citizens in a universe where 400 billion stars are constantly exchanging their most precious substances across the vast distances of interstellar space. The September surge was just the beginning. The real adventure in cosmic archaeology and interstellar understanding lies ahead, waiting for us to develop the wisdom and cooperation needed to read the messages that ancient wanderers like 3I Atlas carry across the dark spaces between worlds.